design of materials for heterogeneous catalysis. Sergey, you can start your talk, I think.
Thank you. Thank you for the introduction. And I thank organizers for inviting me to this workshop. I have an honor to open the session on Friday the 13th, but I promise my talk will not be too scary. So I will talk about computational design of materials for heterogeneous catalysis. And just in case you didn't know, Wilhelm Ostwald gave the following simple, at first glance, and concise definition of a catalyst. So a catalyst is a substance that changes the speed of a chemical reaction without itself undergoing any permanent chemical change. Putting it in other words, a catalyst provides an alternative pathway by which the reaction comes to equilibrium, although it does not alter the position of the equilibrium. So, for example, let's say we have a CO gas and oxygen, and we want to convert it to CO2. However, the oxygen molecule is strongly bound, and so it does not react directly. One has to activate it. Simply speaking, we need atoms, not O2 molecules, to oxidize CO2. So for this, we can use a catalyst. Here is a graphical representation of the same thing. So basically, a catalyst reduces the barrier for a reaction, in particular, the reaction that is useful. Catalysis is used widely in industry, in particular for converting raw materials such as methane, CO2, coal, oil, and biomass into value-added chemicals, fuels, plastics, and medicines. There are two major types of catalysis. Heterogeneous and homogeneous. So in homogeneous catalysis, both the catalyst and the reactants and products are in the same phase, usually liquid, while in heterogeneous catalysis, the catalyst is in a different phase. And there can be different types, solid gas, solid liquid, and liquid gas. So solid gas is the traditional heterogeneous catalysis. Solid liquid is the realm of electrocatalysis, usually, and there are also examples of liquid gas systems. So the heterogeneous catalysis has some advantages over homogeneous, the following advantages. So the different phases allow for an easier extraction of the products, so separation from the catalyst. The path towards active sites is simplified, and the interfaces can serve as carriers for various nanostructures or active molecules. So I will talk about heterogeneous catalysis in this lecture. One of the important applications of heterogeneous catalysis is catalytic conversion of harmful substances from exhaust gases from cars and other sources. So in cars, for example, CO, small hydrocarbons, and nitrogen oxides are produced. They are harmful, and the catalytic converter in a car converts them to less harmful, at least, or not harmful at all, nitrogen, water, and CO2. So here you can already see the challenges of this kind of reaction, that the catalyst should at the same time perform oxidation of CO and small hydrocarbons and reduction of nitric oxides. And the efficiency of such process is high only in a very narrow range of air to fuel ratio, while it would be desirable to do it at at higher ratios, which means a lower gasoline consumption. So the catalysts for this reaction are still sought for. Another very important application is a large-scale production of chemicals, in particular ammonia. So ammonia is produced from basically air, which is 80% nitrogen, and hydrogen. And so this process is called Haber process or Haber-Bosch process. And it's responsible for production of most ammonia, which is used mainly for fertilizers, but also for other in other chemical industries, and also for production of explosives. So you can see on this graph how it grows, the production constantly. So some people say that without this process and without the catalyst for this process, 2 billion people would not survive on our planet. So how this catalyst, the catalyst for this reaction was discovered. The catalyst that is used mainly today is powder of iron activated by some so-called promoters, which are oxides. And it was discovered in 1909 by testing about 20,000 catalysts at BSF, so by postdoc Alvin Mitash under the supervision of Bosch. So, so he really synthesized these 20,000 catalysts and tried them out. So I mentioned the catalytic conversion of exhaust gases is still, there are still some problems to solve, as well as ammonia production, because that reaction at large scale now happens at very high pressures and temperatures. So it's not very energy efficient. But in addition, there are some reactions for which there are no good catalysts, although some of them are done on industrial scale. And here is a list, a short list. In particular, the partial oxidation of hydrocarbons, in particular methane, into methanol. This would be, if a good catalyst is found, this would be a basis for a methanol economy, where we would use methane as a fuel. And also production of so-called syngas, synthetic gas, a mixture of CO and hydrogen. Right now, it's done, again, it requires very high temperatures and pressures. So finding a catalyst that could do it at lower, at more convenient conditions would be better. Then there is the oxidative coupling of methane, which converts methane directly to higher hydrocarbons, ethylene, ethane, and so on. So this is a very pursued reaction. Again, at the moment, conversion of methane is performed to fuel is performed in 2 steps. And this is, again, not energy efficient. Then there is the Sabatier reaction, conversion of CO2 to methane. And so this would allow us to, if we can do it efficiently, would allow us to close the cycle and to recycle CO2 back into fuels. Then a bit surprising, but this reaction is also challenging because of selectivity. Of course, hydrogen just burns in oxygen, so one has to find a selective catalyst for this. But this is also the production of hydrogen peroxide. Oxidation of nitric oxides is reduction of nitric oxides is also still a challenge. And finally, the photo splitting of water. So, catalysis is heterogeneous catalysis is intrinsically multi-scale process. It happens on different scales, and here I show this on the example of catalytic converter. So the catalyst is located here in this part, which is called ceramic substrate or monolith, which is a porous ceramics with pores about 0.5 millimeter. And on the walls of these pores, there is a so-called wash coat. It's some kind of oxide, like aluminum oxide or silica. This wash coat is prepared in such a way that it has high surface area. So there are some pores, very rough surface, and on this surface, located finally catalytically active species, the metal nanoparticles, usually platinum, but also other metals can be used of platinum group. So, and you can see how the scale changes, right, from 0.5 millimeter to nanometers. And finally, at atomic scale, the reaction happens on the surface of these nanoparticles. So, these different scales are connected with each other. And when we try to model a catalyst, a heterogeneous catalyst, in fact, it has been realized in the past 30 years that this connection between the scales cannot be ignored. And in fact, a catalyst is a dynamic material that can appear during the catalytic reaction. And so there is a bit of a catch in this definition. It's a substance that changes the speed of a chemical reaction without itself undergoing any permanent chemical change. But in heterogeneous catalysis, in most cases, we don't know what this substance is. So here is a picture that shows summarizes the different scales, time and spatial scales in heterogeneous catalysis, starting from active sites and chemical reactions at these active sites that happen at picosecond time scales and nanometer or sub-nanometer scale. Then at some larger scales, we have restructuring of the surface or the interface, and then we have segregation phenomena when some components of a complex catalyst, like components of an alloy, can segregate to the surface, and they can form, and particles, for example, nanoparticles can sinter and form larger particles and deactivate. So, so this can happen at very large spatial scale and time scales. And then there are transport phenomena which also affect the catalytic activity and selectivity, transport to site, intraparticle and interparticle transport, and the transport of heat and mass at reactor level. So, and the problem here is that both theory and experiment have challenges to describe this kind of process. In experiment, it's difficult to, so it's more or less easy to measure measure the concentration of products, the reactor level transport and temperatures, but it's not so easy to go to atomic scale, especially at realistic temperatures and pressures. While from the side of theory, and I'm talking about first principles approaches, we can model a single reaction or a surface, but it's hard to go to larger time and spatial scales. So the solution to this problem and to this to address these dynamic changes in the catalyst should be should be addressed from both sides. From theory side, it's development and use of first principles statistical mechanics approaches, and from the side of experiment, it's awareness of these problems and development and use of in situ techniques. So what can we do from theory side? We can use so-called multi-scale modeling, first principles. We start from electronic structure theory, which is density functional theory, or other methods, which can be paired or connected to molecular dynamics. However, molecular dynamics operates or is computationally affordable only between picoseconds and nanoseconds. So I'm talking about ab initio MD. And therefore, we need to, for larger scales, we need some other approaches, and this is kinetic Monte Carlo. I will talk about it a bit more later. And finally, this kinetic Monte Carlo can be coupled to continuum equations, rate equations, and finite element modeling. So when we model a surface, we have to remember that there is a difference between what we model and realistic surfaces, several important differences. This is called, this problem is called materials gap or pressure gap. So first of all, a straightforward DFT calculation corresponds to temperature 0 Kelvin, while in experiments, it's usually not 0. In literature, what is called a surface can be anything between 1 and 5,000 angstrom, depending on experimental technique. Real surfaces are full of defects, such as vacancies, steps, dislocations, and so on. Surface structure and composition can strongly depend on preparation, and impurities and adsorbates can influence the surface morphology. So all this means that a special care must be taken in experiment to produce a defect-free pure surface of known termination. But even then, if we have a reactive gas above the surface, it can react, and at the end we will have a different material there. So we can estimate how many times a molecule hits a site at a metal surface. And here is an estimate. So at temperature 300 K and P equal 1 atmosphere at normal conditions, a molecule hits the site at 10 to the 8th power times per second. So this means that one needs a very low pressure to keep a clean surface clean. But if we have a more complex surface, such as oxide, at low pressures, we can also have, the surface can lose atoms and we can have defects and so on. One has to take this into account. And so the first step is to consider the effects of temperature via thermodynamics. And the point is that at constant temperature, a system minimizes its free energy, which includes this the effects of entropy. If also the volume is constant, then the energy that is minimized is the Helmholtz free energy. While if temperature and pressure are constant, which is more typical for experimental measurements, the energy minimized is Gibbs free energy. So which is shown here, which is also expressed through chemical potentials like this. And so here the chemical potential by definition is, so the sum is over different species in the system. So the chemical potential of species I is the change in the free energy in the system as the number of atoms of that type is increased by 1. So important facts: in thermodynamic equilibrium, the chemical potential is the same in the whole system, and the bulk and the surface in the gas. And the reason why, the general reason why this has to be taken into account, the thermodynamics effects, is that we have a macroscopically large number of particles in the system, and so even rare events eventually happen, and with time we get these important effects of statistics. So in order to take this into account, from first principles, we can use ab initio atomistic thermodynamics approach. Let's consider, for example, a metal surface in the oxygen atmosphere. So the free energy can be written in this way, where we have total energy of the system, which we can obtain from a standard density functional theory calculation. We have vibrational free energy, which we can also obtain from DFT, as you heard in previous talks in this workshop already. Then we have also configurational effects, configurational entropy, which is a challenging part. And until now, actually, you can rarely see in literature that this is taken into account because it's challenging. I will explain. And also a PV term, but this one is usually small. So the we can write the surface free energy in this way, where we have Gibbs free energy of the surface of the slab that we use to model our surface, which depends on the structure and the number of different species, the composition, and the chemical potentials. And for example, if we want to calculate defect free energy of formation, then we can also take into account these effects via chemical potentials. So, so let's consider a particular example, the metal surface with in oxygen atmosphere, and here we have two reservoirs, two thermodynamic reservoirs. For oxygen, it's the gas, which we approximate by ideal gas, and for a metal species, the reservoir is bulk metal, so the chemical potential is equals to the free energy of bulk per metal per atom. And if we neglect for now vibrational and configurational entropy, then we obtain this kind of expression for the free energy. So this we can calculate with, from DFT. These are just total energy differences. A, by the way, is the surface area, let's say area per unit cell, and plus we have this additional term. Delta mu O is just mu O minus an energy, half of the energy of oxygen molecule, which is just a reference. So it's the reference is completely arbitrary. It doesn't change any observables. So so you can see that this free energy depends linearly on the chemical potential, this delta mu O. And so we can go ahead and calculate this free energy for different structures. For example, here I show the P 2x2 reconstruction of oxygen on palladium 100, and here is a surface oxide structure. So that's where we need actually to use some robust algorithm to evaluate energies or to search for stable and metastable structures such as USPECH. because it's important to identify this kind of structures. And then for each structure, we can calculate the free energy of the surface and plot it as a function of chemical potentials. And chemical potential can be connected to temperature and pressure of oxygen via the most easy way is from ideal gas, but it also can be done from experimental measurements for the real oxygen gas and taken from thermochemical tables. So, so what we obtain here is the dependence of free energy, namely the difference between free energy of the surface with oxygen and clean surface. So this dependence are lines, as you can see in this equation. And the surface that is realized in thermodynamic equilibrium at realistic conditions corresponds to the lowest free energy, right? So we can see that at very low pressures or high temperatures, we have a clean surface. Then it converts to this kind of oxygen-covered surface in some narrow range of chemical potentials, and then we start to generate surface oxide until bulk oxide becomes stable. So one has to remember, of course, that we considered a finite number of structures. So in this work, it was considered a finite number of structures, and therefore you can see this sharp transitions, right? But there are, of course, many intermediate structures. They can be present, so these transitions are in fact smooth. And this is the role of, this is where entropy and configurational entropy plays the role, the important role. So we can also consider more species in the gas phase. In particular, in this case, let's consider example of CO and oxygen mixture. So in principle, thermodynamic equilibrium of this system would be CO2. But as I mentioned before, the direct reaction between these two molecules is very slow. Therefore, we can neglect it in the gas phase, but consider on the surface. This is called the constrained equilibrium approach. And so again, we consider thermodynamic effects for now. And in this case, we have free energy of the surface depending on two chemical potentials, right? So linearly on two chemical potentials. This means that the free energy are planes for different structures, particular structures, and the system we consider is ruthenium dioxide 110 surface, which is shown here. So different structures on the surface of CO and O adsorbed at different sites. There are two sites, two main sites, coordinated unsaturated sites, CUS, and bridge sites, PR here. So to understand what kind of surfaces are realized at realistic temperatures and pressures, we kind of look from bottom here. So which surfaces are most stable at different conditions, and we obtain this kind of diagram. This is x-axis is chemical potential of oxygen, and y-axis is chemical potential of CO. These are corresponding temperature and pressure scales. And we find a very intuitive picture which tells us that at low pressure, at very low pressures of both CO and oxygen, we have a surface where the CUS sites are empty, while the bridge sites are covered, are occupied by oxygen atoms. So these oxygen atoms are very stable. However, if we increase the pressure of CO, we start to occupy the bridge sites, sorry, the CUS sites with CO. Otherwise, if we increase the pressure of oxygen, we occupy the CUS sites with oxygen. And at some very high pressures of CO, we can even have the bridge sites also occupied by CO. So, so this is a thermodynamic picture. And if we look at conditions where this system is catalytically active for CO oxidation, we will find that this happens in this region, which coincides with the region where there is on the border of two phases. So this tells us that the catalytic activity is highest when the system is dynamic and is not poisoned. So the sites are not occupied by either only oxygen mainly or only CO. So this is an important understanding. Now, again, this is thermodynamics. Of course, we are talking about chemical reactions. So thermodynamic picture is the first step to understand what kind of changes to expect in the material. But now we have to consider kinetic effects, the reaction, the chemical reaction happens during the catalysis. And so we know molecular dynamics can describe the dynamic effects, how atoms move. But the problem is that the typical barriers for chemical reactions in catalysis are between 1 and 2 eV. These are very high barriers, and to observe transfer of system from one local minimum to the other, the chemical reaction, one would need to run molecular dynamics for a very long time. Most of the time, the system spends in this local minimum. So in order to solve this problem, we need other approaches, coarse-grained approaches, which focus on the important events. And this can be done with ab initio kinetic Monte Carlo. So, so the idea is that if we can calculate the rates of the chemical reaction, then we can solve master equations to determine population of different of reactants and products with time using this so via this coupled equations. And in order to determine rates, we could use transition state theory, where we need these barriers to calculate these barriers for chemical reactions. And also we need to know this prefactor, which can be in fact evaluated from the molecular dynamics. So, so coming back to this example of CO oxidation, so what is needed for kinetic Monte Carlo simulation? So we need to compile a list of elementary processes, which can be a fixed list or it can be determined on the fly. There are also different types of KMC, lattice versus off lattice. In this case, this is a lattice KMC. And we also need to calculate process rates, which are affected by potential energy surface accuracy, and we can use reaction rate theory to do that. So, so for this particular example, the following reactions were considered: adsorption and desorption of oxygen and CO. For oxygen, it was dissociative adsorption and associative desorption, and we also the diffusion barriers, diffusion processes are included, and the reaction. And the transition state theory is used to evaluate the prefactors, and density functional theory to evaluate the barriers for these reactions. Overall, 26 elementary processes, and this is the typical outcome of this KMC run. So this was obtained at temperature 600 Kelvin, pressure 1 atmosphere, and pressure of oxygen 1 atmosphere, pressure of CO 7 atmosphere. This is a snapshot at a particular time. We have certain population of different sites with CO or oxygen. And this is the actual populations as a function of time. And we see that on average, they stay approximately constant, but at given conditions. But there are actually quite significant fluctuations with time. So we can plot these average populations just as we did in thermodynamics case, and we find a diagram that looks similar. There are some differences, but in general, it looks similar. And we find so if we'll now we can calculate the reaction turnover frequency. So how many molecules of CO are consumed per area per second as a function of pressure of CO here. And so the green line shows the calculations and the black line is experiment. And we get a fairly good agreement. It doesn't look that good, but it's actually amazingly good considering the errors in PBE functional in DFT that we get for reaction barriers. So, so there is some cancellation of errors happens here. And again, we note that the reaction is most active exactly in this region where we have dynamically changing surfaces. So, so this is a direct kind of brute force way to solve this problem and to model catalyst and to design catalyst from first principles. But now, so in recent days, years, there is another approach developing, which is connected to data analysis and machine learning. And it was pioneered in catalysis in particular by Norskov, and the idea was that there are so-called descriptors. So there are different properties that we can evaluate, for example, absorption energy or D-band center for a catalyst, but one properties are easier to calculate than others. And in this particular case, to calculate absorption energy of oxygen at metal surface, we need to consider supercell. We need to relax this large supercell with adsorbate and so on. While to calculate D-band center, we just need a clean surface. And what Norskov and his colleagues found is that there is a good correlation between the D-band center and this absorption energy. So in principle, you do not even need to calculate it. You just need to, for all metals, you just need to know it for a couple, and then you can find this correlation and calculate for many different metal surfaces. Similarly, there is a correlation between the energy, the reaction energy, or in this case, CO dissociation energy, and the activation barrier. Again, to calculate the barrier, we need to use some approach like nudged elastic band to calculate in many points along the reaction coordinate and so on. But it's easier to calculate the energy, the absorption energy of C and O and CO. And so that's, again, a similar idea. This is called Bronsted-Evans-Polanyi relation. And approximately it works. So what we see is that simpler properties are correlated to more complex properties. And the simpler properties are called descriptive parameters or descriptors. This model, this D-band model, is in fact based on a simple physical model, Newns-Anderson. At least it motivates this D-band center descriptor. But the question is, what if we don't know such a model? What if we have a more complex situation? For example, some some oxides, on oxides, not just metals or some more complex materials. And also, if you look carefully, of course, on this scale, it looks a good correlation, but one can see that there are deviations between 0.5 to 1 eV, which is, of course, not so small. So, and the idea is that one could use artificial intelligence, including machine learning approaches, to find descriptors. So, formally, a descriptor can be defined as follows. A descriptor should uniquely characterize the material, as well as property relevant elementary processes. The determination of the descriptor must not involve calculations as intensive as those needed for the evaluation of the property to be predicted. And the dimension, so the number of these quantities, should be as low as possible. For example, 1 is perfect, because then we as humans can easily see this correlation. Maybe 2, but it also can depend on the complexity of the system. And the idea is that we could calculate many physically motivated quantities, use these features as a basis for the physical model under compactness constraints. So I guess I should go quicker here. So just briefly, so the machine learning in general, there are many different approaches, and I discuss here particular ones that are suited for finding descriptors. So in particular, regression methods. So regression methods in layman terms is called fitting. We fit our target property, for example, catalytic activity, as a function of our descriptors. And in the standard approach, such as kernel ridge regression, we have this kind of kernel. In this case, it's a Gaussian, so Gaussian function. And the sum is over known data points for which we know the property and the value of the descriptor. And it allows, so if we have a set of data, we can fit these coefficients to reproduce for known properties and then try to predict for the unknown for a given descriptor. And this is an alternative way, a linear regression, where we minimize this kind of list of squares. And here is important term is a penalty, which in this case it is penalty on similar data points, and in this case we have penalty on the number of non-zero coefficients, which is denoted here by as L0 norm, so-called. So this is simply number of non-zero coefficients. So, mathematically, we can formulate it like this. So we have a property as a linear combination of descriptors, and then we penalize this to reduce the number of non-zero coefficients. And in principle, we want to penalize the number, directly the number of non-zero coefficients, but this is a so-called non-polynomially hard problem. Its difficulty grows exponentially with the number of these unknown coefficients. Then there is a ridge regression, which is a sum of squares, but this does not provide most compact representation. And finally, there is a so-called lasso approach, least absolute shrinkage and selection operator, which is a very powerful approach. There is a theorem that states that if we use this kind of norm, which is just the sum of absolute values of the coefficients in this expansion, then we can get, so we under certain conditions, we can get exactly the same result as this one. So, but to do this is a convex problem, is a very easy minimization problem. So, but the condition is that the features should not be correlated. So this is called compressed sensing, this approach. and it's used, for example, for compressing images. You can see these two images completely very different sizes and different scales, but similar quality. So in material science, it became popular in recent years, in particular for example, in cluster expansion, where we represent the energy via energies of certain. So we expand it in terms of clusters with some coefficients, and to find the physically relevant and most important coefficients, and to avoid overfitting. That is, to have too many coefficients that we reproduce some unwanted correlations in the data set. So this can be done with lasso. So we can use lasso to get predictive models in cluster expansion. As I mentioned, the problem is this convex. So the problem is that the features, lasso works very well when the features are uncorrelated, and there is a way to perform compressed sensing a different way, using Schur independent screening. And so this was done in this work. And basically, we generate a lot of different descriptors from an initial set of features with mathematical operators. So it can be billions of candidate descriptors. And then we use this Schur independent screening, which simply correlation between descriptors and the target property. And then we use L0 regularization, the one I mentioned before, to within this selected by SIS descriptors. So, and we applied this approach to adsorption of small molecules on metal alloy surfaces, and we found very good descriptors here. You can see, so these are different kind of alloys, and this is absolute error, and this is what the previous state of the art, the Gibbon center model, gives. So this is maximum errors. These are different levels of errors, and this is our results with CISO. So in conclusion, I hope it became clear that the catalyst design is important and challenging problem. The catalysis is intrinsically multi-scale phenomenon, and catalytic materials are dynamically changing during the reaction. And here where it is important to identify the stable and metastable atomic configurations, for example, with USPECH program at given temperature and pressure. And we can also use the artificial intelligence to bridge this complexity in heterogeneous catalysis. And with this, I finish my talk, and thank you for your attention.
Sergey, thank you very much. Very nice talk. Thank you so much. We have several questions, but we are running out of time, so I will ask only a couple of questions which was raised by Chang. Actually, I can ask him to unmute the microphone and ask his question, maybe. I would like to hear him.
Yeah, that would be good.
Yeah.
Hello, Sergey. Yeah, so yeah, okay, let me repeat my question. So I have two questions. So first of all, you mentioned like a kinetic Monte Carlo calculation. So you mentioned to start, you have to actually list all the important elementary processes for the calculation. So is there any systematic way to enumerate all the important like elementary processes?
So in principle, there are so-called on-the-fly kinetic Monte Carlo, where you can try different, like stochastically, for example, try different processes and evaluate their importance on the fly, and then just discard those that are not very relevant. So, but I would, in general, I don't know any systematic way that would give you all important processes. I think this needs to be explored, at least on the fly.
Oh, so in reality, what do most people do? They do this by chemical intuition, or
the most often you just give the list of processes which you think about, like in this case, right? You have certain sites, you have adsorbed species, and you can think how reaction can go. So that's what is done. I mean, also experiment can provide some information.
I see.
Dear Chang, I think we are running out of time. I would like to ask kindly Professor Shevchenko to maybe, if he can answer, and there are several questions very shortly in the chat, so we can go to the next talk. Thank you very much. Thank you. Okay. Next talk will be by Albert Bulin. He is professor at the Skolkovo Institute of Science and Technology and just professor at the Department of Chemistry and Material Science at Aalto University School of Chemical Engineering. Albert, you can start.
Yes, okay, thank you very much. Can you hear, and please check whether you can see the slide?
Oh, we can see the slide.
Okay, very good. Thank you very much. And so this year the conference is virtual conference, so it's quite unusual. Like if you think so, what kind of conferences we had years ago. There are some advantages and disadvantages in this conference. We can gather from all the parts of the world like easily and discuss the scientific problems. But from the other point of view, I wish to have a really face-to-face conference where I could ask like some questions. I could interact with the audience. If there would be such kind of conference, I would ask, who doesn't have a mobile phone? And I believe that probably everybody would say that they possess some gadgets. The next question would be, who has a Nokia mobile phone? Maybe there would be like a few people who answer, like very few, most likely none would answer that they possess like a Nokia mobile phone. But can you imagine that just only 10 years ago, the Nokia was the most like spread and popular mobile phone. And if I share with you the cover of Forbes magazine, questioning in 2007, can anyone catch the cell phone king? So Nokia, imagine, was like just a few years ago. Now, but where is Nokia now? And of course, they had some difficulties, some problems, some strategic errors. But one of the most important technological one was they did not pay enough attention to the development of smartphones. Smartphones, which could be actually used, which could be developed using the material I would like to tell you about, single wall carbon nanotubes. So I would like to share my experience from Finland to Skolkovo Institute of Science and Technology, almost like 20 years related to this material. Would be just a little bit about the calculations, mainly it is experimental work. And in the beginning, I would like to thank the organizers, especially Artyom Aganov, for inviting me to give this lecture. Elias, everyone whom I get emails from, and also Russian Science Foundation. Thanks to this foundation, that's how we can have this conference nowadays. Okay, my presentation is very simple. I start with a description of carbon nanotubes. I tell about the synthesis of carbon nanotubes and about applications. I don't need to explain very much about it. I think all of you know that, and the easiest way to introduce carbon nanotubes is from the point of view of graphene. You take a graphene sheet, you roll it into a cylinder, and you are going to get a carbon nanotube with different chiralities. Depending on what kind of piece you will take, originally you could get either metallic, semi-metallic, or semiconducting carbon nanotubes. So here you could see examples of showing 1010 and 10.5 carbon nanotubes. I think the USPEC would be quite useful here if you could propose like a catalyst which would allow us to synthesize carbon nanotube with a certain chirality. Unfortunately, nowadays, the synthesis of carbon nanotubes is usually related to a bunch of carbon nanotubes, so where you have a distribution. So you cannot basically produce a carbon nanotube with a certain chirality or metallicity. You always get a bunch of them. Why carbon nanotubes are interesting? So I need to say that this is a recordsman, this is a champion among other materials, keeping like various records. So it is, as a metal, it is a very good conductor, better than copper. It is very nice semiconducting material, better than silicon, and I will prove it today. It conducts heat very efficiently. It could be utilized as a cold emitter of electrons. It's stable up to 1500 centigrade. It is very light and strong at the same time. I don't think that there is any other material which possesses the variety of such kind of properties. And if we look at the applications, practically in any field, we consider, for example, here we see like electronics, photonics, functional, structural materials, medicine, energy, everywhere you will find a niche how the carbon nanotubes could be utilized, either alone or in combination with the other material as a part of the composite material. So instead of just listing different applications, I will show you what we have been working with and where we proved that the carbon nanotubes demonstrate the state-of-the-art performance. Okay, of course, since the lecture is giving the overview about carbon nanotubes, I have to mention and tell about the scientific interest to carbon nanotubes. So unfortunately, the number of publications is started to decrease in 2014. And after that, so I stopped to follow this trend. But the number of patents did not decrease so drastically, so the slope is a little bit less. But if you look at the number of companies who is working commercializing the carbon nanotubes, you could see started to increase quite significantly. The annual growth rate is more than 30%. And that could be easily explained based on the hype of technology. So in the beginning, after the publication by Sumia Ijima, his landmark paper, so people started to be interested in fundamental properties of carbon nanotubes. That's how we see the increase in the interest. After 2014, about 2016, we see that the interest started to decrease. There are many reasons for that. One of those is like graphene appeared, people started to see other two-dimensional materials, they switched. So where we are now here, and I believe somewhere close here, when the interest to carbon nanotubes started to increase because of their real application in real life. So basically, I hope that carbon nanotubes are soon going to be in the market. And last year, I was an opponent of one of the dissertation at Oulu University, and that time PhD candidate Ori Pitkänen, he wrote his thesis, and so he was able to find a proper combination of words to prove that the topic he was working is quite important. Like carbon nanotube plus application, it's still, you see, it's growing. It's good that some people can always find and justify their research. So carbon nanotubes, where are they produced? So mainly multi-walled carbon nanotubes are produced in Asian part. It is China, also Japan, and single-walled carbon nanotubes, probably you all know that the leader is located in Novosibirsk. There is a company, Oxial, which produces tens of tons of this nice material. It is nice also to learn that during last few years, they were able to drop price for these materials 3 orders of magnitude. If 4 or 5 years ago, you could buy 1 gram of carbon nanotube for a couple of €1,000. Now, for the same money, you can get 1 kilogram. I think this is tremendous achievement, and we really hope that these materials soon will appear in the market. What is important that the third of the nanomaterial market is because of the carbon nanotubes. How carbon nanotubes can be synthesized? So I personally divide it into 2 methods. So physical and chemical one, depending on the carbon atomization. So you know that to evaporate carbon, this is physical method based on sublimation and desublimation. You need to put a lot of energy. And this method was very popular in the beginning of the carbon nanotube studies. You could apply the huge amount of energy with arc discharge, laser ablation, solar energy, induction heating. Graphite has a very low equilibrium pressure. That's why you need to heat the source of carbon to the temperatures around 5,000 Kelvin. So there is a very low control over the properties. However, the other method, chemical method, would allow you to synthesize this material at relatively low temperatures. 1,000 is enough. And this method I would divide into substrate supported CVD, where basically you utilize a substrate on top of which you create a catalyst particle, you put it in the reactor, wait 20 minutes, and after that you enjoy your grown carbon nanotubes. And then there is another one, the work which is available maybe in 3-4 laboratories in the world. It is called aerosol CVD method. Some people call it like a floating catalyst, where there is no any support. Carbon nanotubes grow as aerosol particles. And that is going to be a topic of the core of my synthesis method. I would like to tell you about. So we started and developed a few different methods. So from 2002, I believe like 4 or 5 different, completely different reactors. So what's the main difference between them is how we make the catalyst particle and how we introduce it in the reactor. So one way is we utilize tungsten instead of tungsten like iron wire. We resistively heat it to temperature close to melting temperature. Iron evaporates, and then we introduce it to like 300 centigrade surrounding that leads to the formation of catalyst particle. The other way, I probably explain you a little bit in more detail so that you would get an understanding how the aerosol CVD method works. In that case, we utilize the ferrocene molecule. Ferrocene is a metal organic compound, quite volatile at room temperature. By passing carbon monoxide, which plays 2 roles. It is a carbon source and at the same time carrier gas. It goes through the cartridge filled with the ferrocene, saturates with the vapor, about 1 Pascal, and then which we introduce in the reactor. So the vapor of ferrocene decomposes, forms nanometer-sized catalyst particles, 2 to 5 nanometers, and then we have a catalytic reaction on the surface, CO disproportionation, which leads to the release of atomic carbon needed for the growth of carbon nanotube. Flow travels through the reactor during 15 seconds. So this lecture of time you have for all these processes to decompose, to form catalyst particles, and to grow carbon nanotubes, which are collected downstream of the reactor by filtering the flow. So the tubes which are coming from the reactor go through the filter, and we collect them directly on the filter. Depending on the collection time, we collect different amount of the material. This actually provides us different transmittance and different conductivity. And then from the filter, we could transfer it to practically any other substrate. Here is a demonstration. This is a filter which was originally the size of A4. With the scissors, we cut the size of the electrode we would like to have and press it against the secondary substrate. So here we utilize PDMS. So we got elastic substrate. You could also deposit on glass if you wish, or if you would like to make a flexible substrate, you could press it against PED. So the process of manufacturing of the electrode is quite simple and quite quick. So what kind of carbon nanotubes we are producing? If you look in an electron microscope, you would be able to see it is a randomly oriented single wall carbon nanotubes. They contain some amount of iron, which doesn't harm actually many applications, because iron is covered with a graphitic shell, and to take it out, you need really to heat it up to burn the surrounding about the catalyst, and then use chemicals. Otherwise, the iron particles, they are quite good protected. This is randomly oriented carbon nanotubes, no amorphous carbon. The main advantage of this method is that we produce carbon nanotubes in the form we would like to utilize it in the applications. We don't need any purification, practically no treatment. So the quality could be confirmed based on the optical measurements. So for example, the Raman shows a very strong G band, which is responsible for graphitic carbon. Practically absent D band, which is a characteristic of disordered carbon, and the presence of radial breathing mode tell us about the formation of single-walled carbon nanotubes, and shift to the smaller frequencies tells us about the change in the diameter of carbon nanotubes. Raman can see only a tiny fraction of carbon nanotubes. In order to see all of them, you may look at UV visible near-infrared absorption spectrum. This technique allows us to see all carbon nanotubes. For example, on the left side, you could see electronic structure, density of states of semiconducting carbon nanotubes. There is a S11, S22 transition in Van Hoff singularities, and in metallic ones. You could see S11, S22, and also the transition in metallic carbon nanotubes is important. When you change the conditions, you could quite significantly change the diameter of carbon nanotubes, as shown here, the same as the absorption peak, covering the whole range from UV to near infrared, which is quite important for many optical applications. You know that nowadays computers drive our life. Sometimes they help us to live better. We also would like to be in the trend, and we wanted to create the artificial intelligence that would help us actually to control the properties of carbon nanotubes. So basically, utilizing 5 parameters and making the data set. So we used artificial neural network to predict the diameter, yield, and ratio G to D in Raman, which tells us about the quality of our carbon nanotubes. So we were able to prove that our model, artificial neural network, can quite precisely predict what kind of product we are going to get at certain conditions. So applications. We started to work, as I told, in 2002 with the carbon nanotubes. At that time, we did not know what kind of application, so we should select. Looking at the change of electronic gadget, you see there is a tremendous change in the view, look, and the functionality of those devices. And even more changes we expect to happen very soon, when we really get the materials which would be flexible, transparent, and elastic, when the gadget would be possible to bend, to roll it, I mean, to stretch, if you wish. So this material becomes even more important for variable electronics, when we would be able to make a chip which is stretchable, at the same time monitoring the body parameters like heart rate, body temperature, hydration rate, and also the external parameters like UV explosion, those. If we look at the requirements to the materials for flexible and stretchable electronics, we would notice that most likely the process of making of new devices would be on a plastic. So what does it mean? It means that the process of the fabrication must be at room temperature. Of course, it must be price competitive. Therefore, we need to fabricate it at atmospheric pressure with a very high speed, and preferably it should be roll-to-roll compatible. Unfortunately, the existing materials, they do not fulfill these requirements. And the classical example with ITO, indium tin oxide, which is utilized in the majority of electronic devices. For example, in your smartphone. The ITO is a transparent conductor. So the main disadvantage, it is fragile. When you start to bend it, so you are going to break the electrode. You see how the sheet resistance changes when you bend when you increase the bending angle. This will never going to happen with single walled carbon nanotubes. And here is an example which was made with our company, Kanato. It is our spin-off company from the Helsinki University of Technology when I worked there like years back. So they investigated, so how good is material and could it be industrially used for flexible electronics, depending on the substrate. So the best results were obtained, of course, for the thinnest substrate, which is only 23 micrometers. You deposit carbon nanotubes and bend like 180 degree over 2 millimeters curvature radius. So in that case, you could see like 150,000 cycles practically do not change our device. For thicker one, there is like a challenge for thicker substrates. Well, we are talking about transparent conductors. So how good are our transparent conductors? Again, we need to compare it with ITO. Already in 2011, we were able, so the red one, to beat the ITO on flexible substrate. So nowadays we have another goal, is ITO on a rigid substrate, on a glass, for example. It is 10-20 ohm per square. So we have been working like years to achieve, and last year we were able to get like a 17 ohm per square, which is already comparable with the state-of-the-art ITO on a rigid substrate. Of course, again, the machine learning. Can we utilize the machine learning to produce like a good transparent conductors or improve the properties? So for that purpose, we utilized a laboratory scale reactor. So we got a data set, the dependence of sheet resistance at different temperature and different CO2 concentration. So those two parameters are most effective to vary the quality of the carbon nanotubes. And then with support regression, vector regression, so we got a surface of the sheet resistances at the different conditions and found the extreme point, which would predict the best experimental conditions to synthesize the carbon nanotubes. So we got this data for verification. We came to the aerosol reactor. We again grew the carbon nanotubes, and we got like a state-of-the-art performance, 39 ohm per square. So these results are from last year. So machine learning might also help us to significantly improve the properties. Applications. We started to work in 2010 with a touch sensor. In collaboration with University of Texas at Dallas, we made first organic light emitting diode where ITO was replaced with carbon nanotubes. We got a very nice performance. And our company, Kanato, which name came from carbon nanotube, started to improve the transparent conductors in Nokia's phone. And indeed, we made 80 prototypes with Nokia. Unfortunately, Nokia that year was bought by Microsoft, and they lost their interest to develop like a phones, and the R&D was killed, and the Kanato company started to look for their own niche, actually. And I believe that the niche was found the gadget field was quite crowded, and they looked at the automobile industry. If you look at the automobile nowadays, you see that practically any panel could be made touchable if you get rid of like a conventional knobs. So practically with a touching, you might be able to drive your car to change the parameters in your car. So you could deposit carbon nanotubes on a textile, on a laser, on a glass, on a plastic. You could stretch them. You could give any kind of shape. And already a few marks of Tesla cars, they utilize our carbon nanotube as a transparent conductor. So we already see that the carbon nanotubes are coming really to our life. So if you are interested, you could visit the webpage kanato.com. So I just need to continue. Where else we could utilize it? For stable, high efficiency solar cells. Of course, transparent conductors might be utilized as a window layer in solar cells, but additionally, you can dope carbon nanotubes. If you deposit carbon nanotubes on the surface of N-type silicon and P-dope carbon nanotubes, you are going to get a heterojunction between those two layers, which could be utilized to make the solar cell with an efficiency above 10%. So these data were obtained like almost like 6 years ago. Nowadays, people are able to get with the carbon nanotubes close to 16%. So in our laboratory, we worked with amorphous silicon because amorphous silicon allows to get flexible substrate, the same as carbon nanotubes. And so this year, Rajana Pramod, he was a PhD student at Skoltech. So he graduated, published a nice paper with a efficiency, power conversion efficiency of 8.8% for amorphous silicon. If you replace the electrode he developed with amorphous silicon N-type, you get only 7%. So this layer, which is a very difficult and complicated in structure, so allowed to get such high efficiency. It is consists of molybdenum oxide, carbon nanotubes with molybdenum oxide, soaked in P.PSS, and then on top we have PMMA as an anti-reflective layer, and also carbon nanotubes as a fibers. So such kind of complicated transparent conductor has 17 ohm per square and significantly boost the performance of amorphous silicon solar cell. And as you could see, we started with 1.5%, and it took like years to get like to this very high result, good result. Of course, we also, when we discuss about the electronics, we need to ask, can we make a transistor, field effect transistor? And the answer is yes. So imagine this is a reactor, carbon nanotubes are coming from the reactor, they are charged. We could utilize this property by applying a potential to the substrate. We could deposit them. Since part of them are metallics, part of them are semiconducting, we need to create the layer where the percolation between source and drain is not metallic, it is semiconducting. So this could be achieved when you have a very low density of carbon nanotubes. You could make field effect transistors on a rigid substrate or on a polymer. So here you could see an array of 49 transistors on a PET substrate. Of course, the field effect transistors, they are characterized mainly by on-off ratio and by mobility of charges. So here you could see the oval showing the performance of organic transistor, amorphous silicon, and polycrystalline silicon. That's our goal we would like to achieve. In 2011, so we made transistors which were very close in off ratio, 10⁶, but still did not get to the performance to the very high mobility as in polycrystalline silicon. And nowadays we can make the transistors which have higher mobility of charges with a reasonable on-off ratio, which could be utilized for many applications. Quite interesting that the same material could be utilized in two different applications. It could be utilized as a strain-sensitive electrode, as shown here. When you strain it, the resistance goes up. So here is an example demonstration, basically. The current goes through the carbon nanotubes. When you stretch it, resistance goes up, and then the current goes down, and the intensity of the light-emitting diode decreases. So the same material, but prepared in a little bit different way. So this is approach when I showed you the movie. So you take a filter, you transfer it on a PDMS, and the process is done. But if you first pre-stretch the substrate and deposit on a PDMS, in that case, you're going to get wrinkles. So these wrinkles are responsible for the fact that the intensity of the light-emitting diode is not changing because the resistance is constant. That is connected to the fact that those wrinkles, when you stretch them, they become like a flat. The distance between electrodes is practically the same, and we do not see any change in the performance. How we could utilize it? Well, in combination, for example, with a hydrogel and carbon nanotubes, we could make some active components. What we demonstrated, if you deposit on a finger with a pressing finger, you see the change in the resistance. So it could really detect the stretching state. From the other point of view, you could make a passive electrode. So when carbon nanotubes, they just pass the current through, however, do not change their performance. So we demonstrated this with ACG, where we removed copper electrodes and deposited hydrogel with carbon nanotubes and showed that the noise level in the electrodes with carbon nanotubes decreased by 30 decibels. So it is better than the copper electrodes. What else you can do? You could make fibers out of single walled carbon nanotube. For that purpose, you need to soak some solvent like ethanol, for example, and pull the fiber. It is so-called wet pulling technique, and you could make like fibers of randomly oriented single walled carbon nanotubes. Why do you need them? You could utilize them as an extremely sensitive sensor. So one just example, if you located the sensor on your knee, you could detect the heart rate, but also you could see the breathing cycles when the person inhale and exhale. It is extremely sensitive device. So what else can we do? We could make supercapacitors because the carbon nanotubes possess high specific surface area with a very high specific capacitance. But also we could make a stretchable supercapacitors where the size could be increased 2 times, keeping the same performance. So we have like published a series of work related to this topic. And one more interesting application I would like to tell you is using ionic liquid for gating. So we connect 3 electrode cell where the carbon nanotube is a working electrode, there is a pseudo electrode and counter electrode. And when you apply a potential to carbon nanotubes, you basically surround it with the layer of the ions. So basically you create a double electrical layer. And importantly, that you change the Fermi level in carbon nanotubes. This is semiconducting carbon nanotubes, the Fermi level intrinsically just in the middle. When you apply plus, so the Fermi level goes down to some point so that some transitions are not allowed, like S11 is not allowed anymore. You could see here. But you could apply higher potential, you could get rid of S22. So basically you could play with the optical absorbance of this material. But importantly, you could N-dope and P-dope this material. And of course, we are interested in the transmittance of our materials at 550 nanometers, just in the middle of visible range. And we see that we significantly change the absorbance and also when we apply and measure the sheet resistance, we see that there is a tremendous change in the sheet resistance of this material. So totally we could get like 90 equivalent sheet resistance at the transmittance of 90% is 50 ohm per square, which is tunable. You could always decide the optoelectronic properties of your materials by applying a certain potential to carbon nanotubes. How it could be utilized, just be very quick. So if we deposit the carbon nanotubes on a fiber laser, which one side is polished to the core, but carbon nanotubes still affect the light which is going through the fiber laser due to the evanescent waves. So you could, they absorb some portion of light. But if you make a 3 electrode, put a drop of ionic liquid and apply a potential, you might change not only, as I showed previously, the linear properties of carbon nanotubes, but also non-linear. That helps us to make a tunable laser where you could decide what kind of regime you would like to have. So originally we buy the cheap Chinese laser from China. It is a continuous laser, and then when we make it, we could make it a femtosecond laser with a mode lock regime, or with a cool switch, it's a microsecond pulse by applying different potential to the carbon nanotubes. So, and then the last configuration I would like to tell you is freestanding carbon nanotubes. We could make the freestanding carbon nanotubes over a quite large area where the carbon nanotubes just with a thickness of a few nanometers. Here is some application where we already demonstrated as an electrochemical sensor for dopamine, as an air heater. If you pass the air through the carbon nanotubes, you might heat them up. If the carbon nanotubes you apply and resistively heat the film, you could utilize as a filter of aerosol particles, an order of magnitude better performance, quality factor over quite range of concentration. So nowadays, extreme UV lithography becomes quite important because the people would like to make like more devices, and optical lithography is quite important, and extreme UV is coming already as low as like 13 nanometers. But unfortunately, there are no any pellicles, the membranes which would protect the first mask, and second is a source of extreme UV. So our carbon nanotubes could be utilized for this purpose. You could see here is a freestanding film with a diagonal is about like 17, 18 centimeters and thickness of only like a 50 nanometers. You could make bolometers, or you could use it for ultrasound generation. This is the last application I would like to show you, how we could make a freestanding film with a very low thickness. You could see the PET substrate with an opening. We just press it against the filter with carbon nanotubes, and we get a freestanding film with a thickness of like 2010 nanometers. We make an electrode, and then we connect it to MP3 player. So such kind of membrane can play a music. So this music isn't like a simple loudspeaker, but it is like a thermoacoustic generator. How the acoustic waves are produced. You apply a potential, you quickly hit the carbon nanotube film, and then so the air is expanded, then you could cool it down because the film is just only like a few nanometers. So therefore you could create the acoustic waves, which are extremely efficiently produced in the ultrasound region. So we demonstrated that comparing to other materials, so our carbon nanotubes, they produce with a high efficiency and with a very high sound pressure. Yeah, so the bolometers, as I already told you, could be utilized and made like quite quick, quite fast. So I just go through this one due to the lack of the time. And so now I came to the conclusion. I hope I was able to prove that the carbon nanotubes, which are made of by produced by aerosol CVD synthesis, and then the electrodes, transparent conductors made with this way, and then the films, they possess a unique properties which could be utilized in many applications. Since the CVD synthesis is a low temperature, does not require vacuum, very fast, very simple, and at low cost. So at the end, I would like to thank all my collaborators from Aalto University, from Kanatu, like from different universities. And also I'd like to thank the foundation for giving us money to do this research. And I would like to thank my group, Laboratory of Nanomaterials at Caltech, and I would be happy to answer your questions. Thank you very much.
Thank you, Albert. Thank you very much. For now, I don't see any question. Your talk was brilliant and it was very inspiring. Thank you so much. I can maybe ask one question because I just didn't understand. In the last slide, you talked about your nanotube, and you told that we can make the, I don't know, best acoustic sound rather than other nanotube. But I didn't understand, what is that sound for? I mean, how it is important?
How important? It is not important. Probably the thermoacoustic loudspeakers, they will never be important for like audible range where we can hear, because the efficiency of creation of low frequency sound is really like low. But for ultrasound, it might be quite interesting, because if you would like to decide the frequency, it is first of all, it is tunable in a quite wide range. There are no such kind of generators of ultrasound. So at the dual frequency, you generate the acoustic waves, including this ultrasound. So this is a first like a main application. Then second, we can make it not spread in one direction, because we make it from the film. It is it covers like 2 pi actually area. So you could similarly, with the same efficiently, spread the sound into all directions. I mean, that is the main application, or the main advantages of this material. Where it could be utilized, it's a good question. So this material just has been discovered. We just only like revealed the properties of this material. For example, for orientation of robots, like for cars. So if you have it as a source of ultrasound, and then at different frequencies, you can communicate with different robots. So it is quite quick at the same time, so it could be realized. Where else it could be utilized for calibration of ultrasound, because electrically you could decide at what wave, at what frequencies so your sound is, and also the sound pressure. I think that's like quite quick, like proposals for the applications, I could say now.
Okay, thank you very much for your answer. We have one more question. Great talk, thank you. Yes, I was also interested in the ultrasounds production. How stable are these, and do they evolve over time?
Ultrasound again. Was it a question about ultrasound?
Yes.
Yeah. You know, carbon nanotubes, this is one of the most stable materials. So you practically, they do not degrade. Yeah, we have tested it. 1 month continuous use, so there was no any changes in the performance.
Okay, thank you very much.
Yeah,
thank you very much for your talk. So we are going on a 15 minutes break, and then we will have talk by another speaker. So we will see you in 15 minutes.
100 GPa for this study. So we run USpecs. You have seen already how to do it. You have following these lectures on the on-ons tutorials. And at the end, so you will get your ground state structure. And I may say that here, our work in our group can start, because as a quantum chemist, we look at chemical bonding. We like to look at bonds in order to establish a relation between electronic structure and structural arrangement. Then after, when everything is clear, at least for us, the properties may be calculated, such as the electrical conductivity, superconductivity, thermoelectric, elasticity, or hardness. So a few words on the methodologies that we use in this study. So we run DFT, GGA, PBE calculations, but also the scan one in order to have more precise and accurate formation enthalpy. In general, the methodology allows us to get accuracy of 1 millieV per atom in our calculations. So you may have a look at the details at this article published 2 years ago. And we use different codes and tools such as PhonoPy, Lobster to look at the bonding here, but also this old program extended Hooker theory in order to rationalize from orbital interactions the structural behavior and the rearrangement of these predicted compounds. And all of the crystal structures are visualized using Vesta. So I will have to say thank you very much to all of our co-workers, not co-workers, but colleagues who are developing these codes for our community. So we do first a variable composition search. So you have barium here, nitrogen in the other side, and we locate the stable compositions that are lying on this convex hull. We have also metastable composition, as here, everywhere here, above this convex hull, which normally should, from a thermodynamic point of view, this metastable composition should decompose in AB and AB4. But you have to know that this composition, this phase, may be kinetically a stable structure if the activation barrier to go from the composition to AB4, for example, or in another way to AB, is high enough. So we look also at the composition in between this energy window, what I call the viability limit. For this study, we took energy window of 150 millieV per atom, which has been calculated by Cedar and co-workers from their material project researches, taking into account experimental nitrides. And so they show that these experimental nitrides compounds are within these energy windows. And we got this diagram at 50 GPa, where you see different composition along the convex hull here. So you have actually several composition. And for each of them, we run again a fixed composition USpecs jobs to locate the low-lying ground state structures. So you have to do that to be sure that you locate the lowest energy structures at its ground state. So here in one slide, you have a summary, the results of 1 year of work done by Dr. Huang, who was my former PhD student 4 years ago. And you see that USpecs searches lead to all of the experimental composition known for barium and nitrogen, such as the 3-1 composition, the 2-1, the 1,2, and the 1,6, which is actually a side, N3 times 2. And if you look carefully, you have a new composition here, let's say, so it's a theoretical composition with the stoichiometry 3,2, which is well known in this chemistry for magnesium 3N2, for example, and calcium 3N2, but which has never been characterized in the barium nitrogen chemistry. And when the pressure increase, so to 10 GPa, here in green to 50 GPa, then to 100 GPa, you see that other compositions, such as the 110 composition, emerge on this graph. So we found 13 compositions, so quite a lot. Actually, it's a very rich binary phase diagram, and 24 stable phases. So what I mean by stable is thermodynamically stable phases. So for example, let's take this one. So it's a 2-1 composition. So in the black line, it means that you have a thermodynamic stable composition. So from 0 to 100 GPa with 3 different phases. Here are the phase transition pressure that we calculate. And for example, here for the 1,5 composition, you see that you have this dashed red line, which means that this composition is not anymore thermodynamically stable from 0 to 25 GPa and from 80 to 100 GPa. But in between, you have this IMMA space group phase, which is stable for this composition. So in these different compositions, we found several polynitrogen units as isolated atom, so it's expected, so it's nitrides and 3- actually, or molecular species, N2 dumbbells, linear 3-atomic species for small chain here of 4 atoms, and these rings, 5 and 6 rings in these solid state compounds. But also polymeric chain. Here you can see the repeat unit of this polymeric chain, so one-dimensional net running in the sea of cations of barium 2+. And even in this system, we found a layer of nitrogen, you see, with 2 coordinated nitrogen here and 3 coordinated nitrogens, describing a 2-dimensional lattice. So you have here a very rich structural chemistry in this barium nitrogen system. So let's come back to this stoichiometry, the 3,2, which has never been characterized from experiments. So it's an expected stoichiometry, of course, if you count the charge, so which follow here the octet rule for these ions, so Ba2+ and N3-, you should have this 3,2 composition. And we locate 3 different phases from 0 to 100 GPa. So the first one is a C2/M phase, Ba3N2. You have here its crystal structure. So let's have a look. You see here that you have a slab of barium 6 and 4 here with N2 dumbbell within octahedron, Ba6, but also 2 isolated atoms at the center of these octahedrons. So you have slabs, let's say again, stacking along the C direction. So this phase is stable from 0 to 5 GPa. Then you may ask yourself, so you have N2 units within these solid state compounds, what charge is assigned to this N2 unit? So of course you have the answer here, but let's have a look at the density of state just near the Fermi level. As you can see here, we plot the crystal overlap Hamiltonian population. So here in red, you have the bonding level, the bonding contribution here for the pi nitrogen molecular orbitals, and here the anti-bonding one, for example, here and here. And you see that the pi star anti-bonding levels are fully occupied by 4 electrons. So which means that we may assign 4- charge per N2 unit. So which means that formally you have N2 4- isoelectronic to defluorine F2. So now if you count the electrons, if you assign in an ionic model, which is a crude approximation, but we can do that. So you may think that in barium 3 N2, you have barium 2+, 6 times, N2 4-, as I said previously, N3- 2 times, and if you count them, you should add 2 extra electrons. So where are they? So in order to answer, we plot the partial density of charge in this 0, 1, 0 plane. And as you can see, you have an accumulation of charge on the N2 unit here. So here you see it's a prediction of the lone pairs. I forgot to tell you that we plot the partial density of charge between minus 0.5 to 0.0 eV, just below, the Fermi level in this area. And so you have also accumulation of charge on the nitride, isolated nuclei here, as you can see, but also in between the slabs, the Ba3 N2 slabs, the 2-dimensional slabs that you have in this compound. You see that you have a small amount of charge, so which means that you have here localized electrons trapped in voids of these layered materials, which is a sign of for an electride compound. So we explain pretty well the electronic structure and structural structure of this compound. So coming back now to the phase transition and conducting properties. So as I said, from 0 to 5, you have a metallic electride based on N2 and N units with 2 extra electrons delocalized, or I will say, sorry, localized in between the slabs. Then a new phase appears with N3 nitrides, E-1 phase. So you have a salt here, which is semiconductor as expected at this pressure, and above 25 GPa, we have a new phase, C2/C, with nitrides encapsulated in barium. But because of the high pressure here, we observe in the bond structure a S to D transition of the barium atomic levels. So this phase, it's a metal. So we have a metallic electride, then a semiconductor, and finally a metal when the pressure increases from 0 to 100 GPa. So let's focus now on the composition 110. So here it's very interesting to see that between 12 and 100 GPa, we have a thermodynamically stable phase, Ba-N10, which is very interesting for high energy density materials because you have rich nitrogen composition in, so you should have a huge amount of energy stored in this material. So what is this material? Here you have this crystal structure. So you can see that this crystal structure is based on 5-member ring. Here you have 2 rings actually per barium, which correspond to pentazolate and 5-. Here you have the Lewis structure of such a ring with the lone pair here on nitrogen, and the 6-pi delocalized electron on these 5 atoms, which confers stability for this molecular anionic species. It follows the Huckel rule 4n+2 with 6-pi electrons. And as you can see here, the density of state shows a gap between the valence and conducting bonds, as expected for a salt. So here is very well understandable for this structure. So now I will show you few results on the explosive properties of 2 compositions. So barium N4 and barium N10 within 3 phases, and these 3 phases are quenchable. So which means that these high pressure phases remain intact when we release the pressure. So we optimize them again at atmospheric pressure, so 1 atmosphere. There are local minima on their potential energy surface. There are thermodynamically and dynamically and thermally stable up to 900 Kelvin here. Yes. And you see that their detonation velocity are roughly 6 kilometers per second, which is very close to the detonation velocity calculated for TNT, the well-known explosive of Mr. Nobel. So here we potentially have new materials with high energy density storage. Okay, so to summarize this first part, so you see that we predict 13 composition in the barium nitrogen system under pressure with these molecular units, different type of units, which have been observed in other predicting materials with alkaline or other elements, but also one-dimensional polynitrogen nets. And you see that the dimensionality of these polynitrogen nets, which is increasing from 0D to 1D and even to 2D, is related to the valence electron concentration, which corresponds to the number of electrons that you have per nitrogen. So when the number of electrons decrease here, so it means that you may make bonds between nitrogen and get a higher dimensional polynitrogen net. Okay, so let's switch to the second part of my talk, so related to pentazolates, transition metal pentazolate, exactly. So containing these N5- rings. So these results have been published in the manuscript PhD thesis of Dr. Wang, so in 3 years ago. And in this article on the tin nitrogen binary phase system that we investigate last month, published very recently in GPCC. And in coming soon, you will have the pleasure to read what I am going to show you now on the transition metals pentazolate. So investigated by Bowen, Busheng Wang, Frédéric Guégan, and myself here. Okay, So you have to know one thing, pentazolate salts, even if pentazolate is well known, pentazolate salt have been recently characterized experimentally. In CSN5, for example, under high pressure, a work done by Steele and Professor Olenik, Ivan, I think he's watching this lecture. He was at the USPEX workshop in Poitiers that I co-organized 5 years ago. And they predict using USPEX and DFT calculations this composition on the space group of this phase. So it was very nice work. But also pentazolate salts have been stabilized in hydrated materials by Chinese teams recently. So a lot of people are working on this unit as a high energy density material. So here I am interested in this ligand, so it's this molecule, because you see 5 possible coordination sites. Remember, each of the nitrogen has a lone pair, which may interact with a vacant metal orbitals in order to describe the bonding between a metal and the nitrogen. So a ligand here, pentazolate, may be coordinated to 2 metal, to 3 metal, or up to 4 metals, but in a different fashion. Here you have a 1-2 coordination mode, while here you have this 1-3 coordination mode. And you may also have a metal which coordinates 2 nitrogen in a 82 coordination mode. So you may expect a structural diversity when you look at this solid state pentazolate transition metal nets. So maybe we will have 1D or 2D or of course 3D nets in bulk crystals. So let's have a look right now, but you have already the answer. So we investigate a few elements. So here in orange in this slide, this one have been already published by other colleagues around the world. We never published this except barium. And here I will show you a few examples. So with hafnium, iron, iridium, and nickel. Yes, also tin. So the idea is to mix this N5 unit with a structural constraint. We should keep the bonding between the nitrogen during the USPEX simulations. So to do so, we use the molecular crystal evolutionary algorithm approach. So here you have a copy screen of this input file. So you should use the keyword 310. And you have to define the 2 components of your molecular crystal in this case. So I choose nickel N5 2 times. So here you have to write 1 for nickel and 2 for 2 pentazolate units. Then you will define 2 files, mol1 and mol2, with the Cartesian coordinates of each component. So here nickel, so simple 0, 0, 0, and the Cartesian coordinates of the 5 nitrogen atoms, which are here. So remind that you have to correctly define the Z matrix for this given molecular species. So in all of our predicting and optimized pentazolate transition metal compounds, we found that the nitrogen-nitrogen distances are in between 1.30, 1.35 angstrom, which is characteristic to a single double bonds as expected for this pentazolide with this delocalized 6pi electron. So nothing new here. On your left, I plot a molecular orbital diagram between the molecular levels of N5 minus here. So here you have the bonding and non-bonding occupied levels. And here the first anti-bonding vacant, empty levels, which interact with the 9 valence orbitals of a given transition element. And you see that in general, we will get a material with energy gap leading to a semiconductor or insulator. So I'm not going to talk about the conductivity in these materials later on. So the first, sorry, the first example is the one which contains 20 nitrogen per metal in HFN5 4 times. In fact, you have oxidation number 4+ for hafnium. So we may mix it with 4 and 5- units. And here you have its crystal structure. You see that you have polymers running along this perpendicular direction of your screen. And here you have a look at this polymeric chain. So here you have 1 unit. And you can see that you have these 4 and 5 units coordinated to 2 metallic centers. So each hafnium is in a square antiprism site. It's a ML8 fragment in a square antiprism with an electron count of 16 for a D0 HF4+. This is very well known in organometallic and coordination chemistry. We look at another cations. Here is iridium 3+, and we got at atmospheric condition this iridium N5 3' compound with a polymeric crystal. So here it crystallized in the P6/3/M group with also a polymeric chain here, but this time you have only 3 pentazolide units bonded to 2 iridium cations, and each iridium is coordinated to 6 nitrogen and sits in an octahedral site, which is expected for this 18 valence electron ML6 D6 compound. So maybe you don't know how to get this 18 counts. So remember, you have a lone pair on each nitrogen. So you have 6 nitrogen, 6 times 2, 12, at least in France, plus the 6 valence electron of iridium 3+, so which leads to the usual electron count of 18. Next compound, so we look at nickel, palladium, platinum, but here I will show you the results for nickel. So between 0 and 50 GPa, we got only a single phase, so it's P21/C, which presents this beautiful crystal structure you see here. You have a layered material, so with a 2D lattice, with pores of around 5 angstrom here. Each pentazolide unit is coordinated through this 1-3 atomic number, I mean, fashion. The nickel sites are surrounded by 4 pentazolate in a square planar configuration, as expected for a 16 valence electron ML4D8 complex. So when you see these layered materials, I am sure that you say, okay, guys, maybe we can cleave this layer in order to get a two-dimensional compound, a nickel, cyclohexane 5 2 times. And actually, it's what we look at. So we optimize in vacuum this layer, so which is dynamically stable, thermally stable up to 900 Kelvin. And we compute, we calculate the cleavage energy using the scan RVV10 level of theory. So here is to take into account the van der Waals interaction in these layered materials. And we got a cleavage energy of 0.18 kilojoule per square meters, which is half of the value found calculated in graphene. So we think that if one can synthesize these bulk layered materials, we may also get these two-dimensional nets. But take care, it's an explosive material. And yes, oh, iron. So iron is very funny here because actually I start to look at this chemistry because of this article written by Franklin Gerling. So 20 years ago, he proposed this molecular species analog to ferrocene, iron C5H5 2 times. So you see here, you have iron with 2 5 member ring sandwiching this iron atom. And it proposed that this iron N10 molecular compound is stable. So it's a very rich, high energy density material. So we test it using USPECS, and as expected, actually, we did not get this molecular species, fancy, but very unstable at plus 5.5 EV per mole, higher in energy that the metal inorganic framework that we found in this R3 structure. So you see here that you have voids, also pores, and you have iron sitting in an octahedron of 6 nitrogen atoms, as expected for this electron count. So what's happened when we increase now the pressure from 0 to 50 GP? And here you see that you have a phase transition at 14 GP. And we get this structure. It's a layered structure. As you can see here, you have a slab of iron N5 2 times with, look carefully here, the pentasolate unit coordinated to 3 iron sites. Each iron is also 6 coordinated to 6 pentasolate. And this high pressure phase is quenchable. So which means that it remains this layered structure with a separation of 2.53 angstrom between 2 slabs at atmospheric pressure. But this metastable structure is 60 millieV per atom, higher in energy than the R3 phase. Okay. Yeah, here is just to show you that we investigate also the combination of pentasolate with a p block element as tin. So tin, usual oxidation number is 4+. So you may have 4 N5 minus units, but also 2 for the oxidation number of 2, and you will get at high pressure this metal inorganic framework, and at low pressure this layered material. So I will close my lecture now, but I would just to say that our predicting polynitrogen materials may look fancy to the community, especially for the experimentalist people. But recently, our predicted high pressure compounds, such as titanium N2 and magnesium N4 composition, have been experimentally characterized under high pressure. So we are really proud of our USPEX DFT simulations now. So to summarize, here are the polynitrogen nets that we describe in this polynitrogen salts and polymeric, let's say, coordination polymers. And you see that we got several type of structures with these covalent nets of with 1 dimension, a 2-dimension layers here, or a 3-dimension, as known in metal inorganic frameworks. Finally, I would like to acknowledge my great team of Poitiers. So here you have Dr. Busheng Wang. He will be your lecturer this afternoon for the tutorial on USPEX 2D materials. Rabi Larlimi and Heng Zhang are my PhD students. Heng is also a PhD student at NPU with Artem, and under the supervision of Professor Wang at so the Northwestern Polytechnical University. And recently, we have a new member, faculty member, so Professor Frédéric Guégan, who joined my group, and is mainly working on chemical reactivity and conceptual DFT, which may allow us to find new descriptors for the fitness of USPEX investigations. And of course, I have to mention my collaborators. So now Bowen Wang is at the Hunan University. And also I would like to thank Hubert Valencia, who is working at Nagoya University in Japan. And he just created a startup in high performance applications. So if you have, of course, money and works to do in high performance application, please, he's a nice guy. You will show his code GDIS to analyze the USPEX results this afternoon. And of course, I would like to thank Artem Oganov. So we worked together since 10 years now, yeah, already. So money. So let's focus on this French institution, GENCI. So for the allowance of computational resources, without these national public centers, I will never do what we can do in my group. And we have support from our region, Nouvelle-Aquitaine, so it's near Bordeaux, CNRS, and so on. Okay, so now few lecturers think that it's a great thing to be in this virtual space, but personally, I do not like at all. I prefer to be face-to-face, to share with my colleagues information, scientific or not. But I hope that in a real space, future machine learning crystal structure prediction workshop will be run in Poitiers. So please, now waiting for your comments and questions. Bye.
Thank you very much, Gilles. Thank you. It was really good lecture.
Okay, so now I have to come back for the screen.
There is one question. Nitrogen-rich materials. The question is, which metal do you suggest with nitrogen can form polymetric nitrogen at low pressure, possibly at ambient pressure? And second, did you calculate energetic properties for nickel, iron, and tin based petazolites?
Yes, so I try to show the question, but I can answer. So first, yes, of course, we calculate. So live, where is it?
You can see, yeah, you can see yourself the questions, of course.
No, I don't want to, I know I cannot because I do not have the, anyway. we calculate the explosive properties of these transition metal polynitrogen compounds. I did not mention them because it was too long, but yes, and they are actually better than the ones we calculate in alkaline earth metals. So here is the second part of the question. The first part I forget already.
The first part was, which metals do you suggest with nitrogen can form polymetric nitrogen at low pressure, possibly at ambient pressure?
At low pressure, so we investigate magnesium, barium. So you may have these nitrogen-rich materials with these two elements, and of course nickel. We just saw here that nickel is stable at ambient pressure with pentazolate. So now the big issue is how to synthesize pentazolate with nickel. So one may start from azide nickel mixed with N2 and using laser heating, for example, under pressure, you will couple N3 minus with N2 given N5.
Okay, thank you very much. We have a couple of more questions, but we are running out of time. Maybe you can answer them in the chat if you found it. Thank you very much.
Yeah, see you, Zaid, and see you guys. Bye.
Let's go to the next speaker, Dimitri Semenok. He's a PhD student at the Skoltech University of Science and Technology, Institute of Science and Technology, and he will talk about high temperature superconductivity in ternary hydrides. Okay, Gilles, still I think you're, yeah, hello. Still, I see the presentation of Gilles on the screen.
Attends, moment. I have to leave.
You need to stop.
No, fuck. Bon, attends. I switched down my computer. Yeah. It's a French way. It's a French way. Don't worry. It's okay.
Do you have a button stop sharing? It must be red.
Don't.
Okay.
Wow.
Okay. He will come back.
Different button.
Okay, start, dear Dimitri.
Okay, almost. Okay, can I start? Can you hear me?
Yeah, sure.
Okay. Okay, let me just So hello everyone, my name is Dmitry. I'm a PhD student in Skopje Institute of Science and Technology, and today I will focus on recent advances in high temperature superconductivity in ternary hydrides, because in the previous talks within this workshop, Artem Aganov and Alexander Kvashnin and Ivan Kruglov already discussed the binary hydrides. So in this talk, I will concentrate on ternary hydrides and its superconductivity. And let me say firstly a couple of words in introduction. Actually, superconductivity surrounds us. And for example, all medicines that we can buy in the pharmacies and all medicines against this COVID virus were synthesized with using nuclear magnetic resonance spectrometer and were analyzed using this device to determine the exact consequence of the atoms, carbon, hydrogen, boron, nitrogen in the molecules, to determine the structure of molecules in order to develop new medicines like favipiravir, remdesivir against this disease. And the key point, part of this nuclear magnetic resonance spectrometer is exactly a superconducting coil. Another application of superconductivity is synchrotron research. Synchrotron research allows us to obtain very intensive and very precise focused the X-ray beams to analyze a single crystal diffraction, to determine also the structure of biological molecules, macromolecules like proteins, and to understand how the bacteria or viruses or ferments, human ferments works. It also have some application in magnetic field sensor to construct the magnetic field sensors, computers, and in maglev trains, and in many other applications like single photon detectors and so on. And superconductivity actually has come a long way since discovery of first superconducting materials. Mercury by Cameron Onnes in 1985, and the first about 20 or 30 years, people mostly studied the pure metals, and the best pure metal, niobium, was found, and it has critical temperature superconducting transition about 9 kelvins. And after the Second World War, the people studied the binary systems, and significant progress has been achieved. And the intermetallites, niobium, stannum, and for example, niobium, germanium, vanadium, silicon were found, and the TC critical temperature was increased to maybe about 20 kelvins. After that, the revolution has happened, and in 1986, new class of superconducting materials, cuprates, which consist of 3, 4, or even 5 different atoms, were discovered. This class was discovered, and the critical temperature achievable in this class of compounds was increased to above 150, 160 kelvins. And just recently, 5 years ago, another revolution happened, and the superconducting hydrides were discovered, and the first superconducting hydride was sulfur hydride H3S with critical temperature above 200 kelvins under pressure, and this value of critical temperature was much higher than all critical temperatures found in the cuprates class. So it was a very significant step forward in development of new superconducting materials. And such properties of hydrides, of compressed superhydrides, are due to presence in their sublattice, in their structure, metallic atomic hydrogen sublattice. In a pure form, when we compress a hydrogen, it also can be obtained, but at extremely high pressures, about 500 GPa, it's 5 million of atmosphere. So when we compress a pure hydrogen, and it finally will become a metal with also quite high predicted critical temperature of superconductivity, about 200 and maybe close to 300 kelvins. But unfortunately, it requires huge pressure. 5 million of atmosphere is very complex to reach, and typically people, only a few laboratories in the world can reach such pressure. And it was discovered in recent maybe 10 years. It was discovered that it's much simpler to obtain this sublattice, metallic hydrogen sublattice, in combination with other elements, in chemical compounds with other elements, which is called the hydrides. For example, in sulfur hydride H3S, which requires only quite relatively small pressure, 150 GPa. It's 1.5 million of atmosphere, approximately 4 times lower than the pure hydrogen. And at this pressure, this sulfur hydride demonstrated superconductivity at about 200 kelvins, demonstrates superconducting transition approximately this temperature. Another example was synthesized 2 years ago. It's a even much better superconductor. It's a metallic lanthanum H10 decahydride of lanthanum decahydride, which was firstly predicted theoretically. The convex hull was calculated using the evolution research methods, and authors of this paper in PNAS found that composition lanthanum 1H hydrogen 10 should be stable at pressures above 150 GPa, and approximately at this pressure, it was experimentally found 1 year later. It was experimentally found in 2 groups, in America and in Germany. This compound was synthesized, and it demonstrates superconductivity above both. So it's a extrapolated upper critical field over above 100 Tesla. And superconductivity in this compound can be described in the classical Barton-Cooper-Schiffer model and using Migdal-Ellsberg formulas. It can be described completely, so it's a classical superconductor. Let me say some words about preparation techniques, because here in Moscow we have opportunity to direct validate for validation of our theoretical predictions. For example, we have some theoretical prediction, and we have opportunity to do experiment and validate our theoretical results immediately after prediction, after theoretical study, theoretical investigation. So the typical, if we want to synthesize such a superconducting hydride, superhydride, we place a small sample of metal on the diamond anvil, on the diamond anvil, and after that connect this sample by 4, 5, 6 electrical leads to study the electrical transport, to do the electrical transport measurements. And after that, we compress the sample using the gasket as a walls to isolate the chamber, high pressure chamber, the region where the high pressure will be reached, by a metallic gasket, tungsten, rhenium, and compress it by another diamond anvil. So this is, for example, the picture how it looks like in reality. And the typical sample that's studied in this method has a diameter about 30 microns, maybe 50 microns. And this is a cell already assembled diamond anvil cell. You see the diameter of the cell is 5 centimeters, but in principle it can be reduced to maybe 1 centimeter. So it's quite a small device. The key elements of this device is very expensive diamond anvils, of course. Unfortunately, they cannot be saved, and that's why during this experiment they typically broke, and it makes the experiment quite expensive. Makes the experiments with high pressure quite expensive. And now in Moscow there is a collaboration of several institutes that allow us to do this not only theoretical investigation in Skoltech, but also the experimental investigations of predicted materials in Crystallography Institute of Russian Academy of Science, where we can assemble diamond anvil cells and prepare laser heating to synthesize these superconducting materials. And we have also collaborate with Lebedev Physical Institute, with Ginsburg Center of Superconductivity, to do the transport measurements in the high magnetic fields and to measure the critical currents in samples. And determination of structure, we are doing determination of structure in Europe, on European synchrotron sources like ECRF and day3, Petra in Germany, and also in Japan and in China sometimes. So it's necessary to use a synchrotron because the samples are very small, and we use a synchrotron diffraction to determine the position of heavy atoms. Position of hydrogen cannot be determined. And at this moment, so this is the current progress of research. At this moment, 12 binary metal hydrogen systems were studied. It's all such metal hydrogen systems can be divided by 3 classes. Approximately, it's a molecular hydrides, which are typically semiconductors, do not conduct the electric current. Another class, it's a metallic hydrides. Typically, they demonstrate a superconductivity. Some of them are very close to room temperature superconductors, to be room temperature superconductors. It's a yttrium H9 and lanthanum H10. And another class, it's a magnetic metallic hydrides, where the magnetism completely suppresses superconductivity, and they mostly do not demonstrate any superconducting properties. A significant part of this studied 12 metal hydrogen systems were investigated here in Skoltech or together with our, in collaboration with Jilin University in China. So we studied praseodymium, neodymium, europium, barium, cerium, thorium, and uranium and yttrium hydrides. So it's a significant part of all known and all studied at this moment binary metal hydrogen system, binary metal superhydrides. And during this investigation, we determined that we figured out how the superconducting properties distributed in metal binary hydrogen systems and binary hydrides. And we figured out that actually there is very narrow class of materials, very narrow class of metals that can form high temperature superconducting hydrides. They all they all belong to the D1 and D0 belt, or we can say it's a superconducting belt or lability belt. And this narrow class of metals, only this narrow class of metals can form high temperature superconductors. The situation with ternary hydrides is much more complex. It's much more complex because the total number of systems is about 4,600, and we do not have a lot of even theoretical investigations. We have just a few theoretical investigations of such systems. And in this situation, it's a common way to apply artificial intelligence, to apply the maybe neural network approach to determine the maybe even approximate distribution of superconductivity in ternary hydrides. We did it, and we used a physical model with physical meaning. Let's imagine that we have two metals. One metal is A, and the second metal is B, and we put a alloy of these metals on the diamond and we'll kill it and load by hydrogen. After some experimental efforts, we can define the best concentration of element A, B, and hydrogen in this system, the best pressure, the best hydrogen content, and define the function which I will call which is called the maximum TC. Oh, I can call it maximum TC, and this function will depend only on two metals and on parameters of these two metals, two elements A and element B. Unfortunately, we do not have too much, as I said, maybe just 15 systems we already studied, and superconductivity and the structure and dynamical thermodynamical stability was studied only for 15 systems. But we can add to this investigation about 50 or maybe more already studied binary systems as degenerated ternary. So if the A is the same as B, that will be a binary system, and we can consider it as a degenerate ternary system. It helps us to build this neural network and obtain the distribution of superconductivity in ternary hydrides. Of course, approximately. Of course, it's not maybe very reliable data, but this is the first step, first approximation, because we do not have anything, and we need to select system for experimental research for next experimental steps. And this approach shows us one very important thing, that all high temperature superconducting ternary hydrides can be constructed, can be built from the best binary metals, from elements from this D belt or superconductivity belt. It's the most important, the main conclusion. And in fact, the result of work of this neural network is like a table. So initially we had about 4,600 systems. And finally, we narrowed it to 48 the most perspective systems, which should demonstrate, according to this neural network algorithm, should have a TC over 250 Kelvin. So they are promising for experimental research. Experimental research is very expensive, so we should care about the system we select for investigation. And for example, for lanthanum, the system predicts that the combination of lanthanum with lithium, magnesium, calcium, and yttrium, especially yttrium, gives the maximum, the best superconducting parameters for the ternary hydrides that can be obtained from this alloy, from alloy of lanthanum and yttrium, lanthanum and calcium, lanthanum and magnesium, and so on. And for example, for lanthanum, I put here the table, not the table, but picture. Dependence of maximum TC, this function that we predicted by using this neural network, and the atomic number of elements. And you see that this is a lanthanum H10 point. And if we consider the system and study the system scandium, lanthanum, hydrogen, calcium, lanthanum, hydrogen, we should get the better TC. We should have should obtain a better superconductor. Another approach is direct substitution of metal atoms in already known superhydrides, like already known and very good superconductors, high temperature superconducting superhydrides like lanthanum H10. It's a cubic structure where we can replace part of the atoms of lanthanum by, for example, yttrium or zirconium or scandium. And the same for cubic yttrium H6, where we partly can replace yttrium atoms by other atoms, by lanthanum again, calcium, magnesium, and so on. And investigation and calculations using quantum espresso directly shows us that the conclusion that we obtain from neural network is actually correct. And direct calculation shows that really quite high critical temperatures can be achieved in these structures, ideal structures, when we replace the one atom by another atom. Moreover, we got another conclusion and suddenly discovered that this metal atom like yttrium can be replaced by non-metal atom like tellur, bismuth, stibbium, maybe arsenicum, germanium, and other atoms. And even inert gases can be used to stabilize the clatrate structure, the hydrogen cage, to stabilize hydrogen cage and to obtain high temperature superconductors. For example, for lanthanum H10, we can replace some atoms of lanthanum by neon, inert gas, and still this compound may be high temperature superconductor. And according to calculations using Allen-Dynes equation, Allen-Dynes formula, should have a TC about 239 kelvins. For yttrium, the best result for yttrium H6, the best result can be achieved when we replace yttrium by tellur. And the prediction shows, gives us TC about 285 kelvins. So this is another group of elements which in combination with yttrium, lanthanum, and other metals can give us high temperature ternary high temperature superconducting ternary superhydrides. It couldn't be predicted by neural network because neural network actually just interpolates the data that we already have. This data is new data. And we decided to investigate one ternary system theoretically and experimentally. It was the most, the most obvious example. It's a lanthanum yttrium hydrides. So the two best metal hydrides, it's a lanthanum H10 and yttrium H10, were mixed together, and we studied this system in order to improve maybe superconducting properties of lanthanum H10 and get a better superconductor. So we first studied the convex Hall thermodynamical stability of ideal FM3M and ideal IM3M, so PCC and BCC structures of such hydrides, where we just replace part of lanthanum atoms by yttrium and part of yttrium atoms by lanthanum. And we found that actually several such ternary ideal cubic systems, ideal cubic compounds, are on the convex Hall, especially when we increase temperature with accounting of configurational entropy. And at temperature above 100 kelvins, a lot of such compounds become stable, come to the convex Hall and are placed on the convex Hall, and probably in principle can be synthesized. They are stable dynamically and thermodynamically too. And calculations of spectral Lie-Ashberg functions also shows that they are very promising. It's very promising to synthesize such alloys and try to synthesize such hydrides. For example, lanthanum yttrium H20, the cubic hydride should have a TC above 266 Kelvin according to the predictions. So the experiment was planned and has been done for such systems. We prepared several lanthanum yttrium alloys. Initially, alloys are hexagonal, but after heating with hydrogen, with ammonium borane, which is used as a source of hydrogen at high temperature, the compounds with ideal cubic structure were synthesized. Absolutely ideal cubic structure. Those obtained hydrides have absolutely ideal cubic structure, FM3M, and the volume, unit cell volume calculated from X-ray diffraction data shows that it contains both type of atoms. It contains lanthanum and yttrium together. And because there is a yttrium surrounded by the hydrogen cage, which is similar to yttrium H10 compound, pure yttrium H10. This compound should demonstrate, this part of compound should also demonstrate the critical temperature close to room temperature, according to the predictions, according to theoretical calculations. At lower content of hydrogen, we synthesized IM3M, ideal IM3M crystal, ideal IM3M hydride, with content of hydrogen close to 6, and composition of this compound is approximately can be described as a lanthanum to yttrium H18. Because all of these compounds are solid solution, we cannot see the reflections from the yttrium sublattice. We cannot see it. We can see only the main reflections from the lanthanum, because the lanthanum is much heavier and it scatters X-ray beam much better than the yttrium. So we see only the lanthanum and yttrium just randomly distributed in the sublattice of metal sublattice of lanthanum in this superhydrides. And there is only one difference. It's a unit cell volume. An analysis of equation of states of these compounds shows that actually the volume of obtained compounds are below pure phase of lanthanum H10 and lanthanum H6, which is shown on here in this diagram. The experimental points are much lower, and they are at the same time much higher than the pure yttrium phases, and they very well correspond to the predicted equation of states for mixed hydrides, for lanthanum 2 yttrium H18 or lanthanum 3 yttrium H40, and can be described using this composition, using this chemical formulas. These compounds demonstrate the superconductivity. It's a high temperature superconductors. Extrapolated critical fields is above 100 Tesla. And critical currents is above 300, I showed it here, 3,500 ampere per square meter, which is much higher than for cuprates, for niobium-tin intermetallites. And the superconductivity of this compound at this moment we reached 253. We continue this experiment, so we need to find the optimal pressure. So now we investigated just the several pressure points, and I think the critical temperature will be increased in this alloy, and the resistance obviously dropped to 0, especially in these pictures. Yeah, more than in decreases during this superconducting transition, decreases more than in 1,000 times, more than 1,000 times. And the last ternary systems that I want to describe in my presentation, it's a recent publication in Nature, very important publication breakthrough. It's a discovery of room temperature superconductivity in the carbon sulfur hydride, in the carbon sulfur hydride system, where the authors described and discovered the superconductor with critical temperature about +15 up to +15 Celsius at quite high pressure. But anyway, it's very important. The only one question that all authors, all other scientists asked them: what is the structure of this compound? What is the structure of this superconductor? Because if we do not know the structure, we cannot calculate anything. Cannot study electron structure, cannot study superconductivity, cannot calculate TC. And as many groups, as other groups, we performed a theoretical investigation of this system and calculated the three-dimensional convex holes together with two-dimensional. Of course, it's possible that this is binary hydride, just sulfur, hydrogen, higher hydride, superhydride of sulfur and hydrogen, but we also calculated three-dimensional convex holes. As you can see on this picture, the most stable compound is still H3S, a cubic H3S that was discovered in 2015, but this compound cannot explain the so high critical temperature of superconductivity. Another compound that was also found by evolution research, it's carbon sulfur H7. It was published in PRB in this year, 2020, where the one sulfur atom just replaced by methane molecule. However, introduction of this methane and replacing the sulfur by carbon leads typically, in most cases, it leads to decreasing of critical temperature, and superconducting properties become worse such compound. In fact, in our search, we didn't find any stable ternary hydrides, and mostly all found by evolution research ternary carbon sulfur hydrogen compounds, carbon sulfur hydrides, have positive formation enthalpy, and only one compound has negative. This is described as carbon sulfur hydrogen 7. Anyway, it's very interesting to study even maybe thermodynamically unstable phases to determine maybe which structure can give us such high superconductivity, such high TC, which is close to room temperature, which is close to 300 kelvins. And we studied unstable structures. And for example, for pure sulfur hydrides, for binary sulfur hydrides, we found the sulfur 2H7 as one of the closest to convex hull, the candidate which is close to the convex hull. It contains one-dimensional long, one-dimensional hydrogen chains, HHH. Unfortunately, these chains do not lead to any pronounced superconducting properties in such compounds, and this compound is actually very weak superconductor, TC even below 100 kelvins. We studied another candidate. It's a ternary candidate, sulfur carbon H16. It's a very unusual compound. It contains some kind of fragments or molecules. We can even call it molecules. Carbon H8 and sulfur H8. Quite fantastic compound. Which anyway, its predicted TC is quite high, 246 Kelvin. So this compound, or maybe this structure, is a promising candidate to explain the room temperature superconductivity in such hydrides. There is another candidate again where we replace one sulfur atom in H3s by carbon atom, but it has different structure. Content is also free, and it's a cubic crystal, very high symmetry. It looks very nice, but unfortunately, the replacing sulfur by carbon, as I told before on the previous slide, typically leads to decreasing critical temperature. So this superconductor is much worse than H3s, than pure H3s. So this candidate doesn't work. So this is a bad candidate and this structure cannot explain the room temperature superconductivity. So finally, I will pay attention on the third candidate that was found in NPU by our friends in Xi'an, by Haiyang New group. This compound has the same composition. It's a carbon sulfur H16, but it has hexagonal structure, hexagonal symmetry. And it consists of two-dimensional layers of hydrogen, graphene-like layers of hydrogen, which is stitched with polymer chains. This polymer chains is a sulfur carbon H3. Carbon H3 is a common for organic chemistry, very stable group. And after that, it's just repeating many times. And this polymer just stitched the layers, all hydrogen layers together. And this compound can explain the room temperature superconductivity in this in the carbon sulfur hydrogen system. Let me explain how. In common metal hydrides, we have a metal sublattice and the hydrogen sublattice. And phonon transfer is prohibited, and typically the phonons from metal sublattice cannot be transferred to hydrogen sublattice. Because of huge difference in the masses. Mass of hydrogen is 25, maybe 50, maybe 100 times lower than the mass of heavy atoms like lanthanum, yttrium, scandium, and so on. And typically transfer doesn't work. Phonon transfer doesn't work, but electron transfer works well. So the electrons from the metal sublattice mostly go to the hydrogen sublattice due to big difference in the electronegativity. When we have to deal with these polymeric chains in this structure, carbon sulfur hydrogen 16, we have light elements. It's a sulfur and carbon, and the ratio between the mass of carbon and mass of hydrogen just 12. So it's very easy to transfer phonons, low frequency phonons, to the hydrogen. Much easier transfer phonon phonons from these polymeric chains to the hydrogen sublattice, until the intermediate frequency range about 10-30 terahertz, which is critically important for high temperature superconductivity. And in fact, the graphene-like hydrogen layers stabilized by infinite polymeric chains with pentacoordinate carbon may be responsible for this room temperature superconductivity in this discovered carbon sulfur hydrides, as I show on this slide. In fact, there are Gearing nodes. These CH3 groups can give us some kind of topological connection and force the layers of hydrogen oscillate with the same frequency as the frequency of oscillation of polymeric chains. So it's like modulated vibrations, modulated oscillations of the hydrogen transport layer with the frequency about 10-30 terahertz, which provides very good connection. This mechanism provides very good connection between the polymeric chains and the hydrogen layer, and provides very good phonon transfer to the hydrogen layers. Direct calculation in quantum espresso shows exactly that, exactly confirms this conclusion that critical temperature in such compounds, in such systems, which are very universal, because we can replace the polymeric chains carbon-sulfur by any other polymeric chains like carbon-carbon, like polyethylene, polyacetylene, boron-nitrogen polymers. There are a lot of hundreds, thousands polymers that already discovered, and we can introduce it in the structure of metallic hydrogen, introduce a layered structure of metallic hydrogen, or maybe any other two-dimensional materials. We can introduce it and get very good superconductor. Okay, and the calculation of electron structure shows also presents a lot of one-half singularities close to the Fermi level in this compound, and you can see that on this plot of density of electronic states, you see that Fermi level is very close to the series of one-half singularities, which is very important for high temperature superconductivity. Let me finish my presentation. And the main conclusion that I want to say that I'd like to say that world of Avatar becomes a reality, and with its flying mountains and flying rocks. And this is end of my presentation, but this is not the end of the story. So we will continue work on this system. So thank you very much. I finished.
Thank you very much, Dimitri. It was really brilliant. Thank you so much. We have some questions. Question from Lucas. Thank you for your talk. I would like to ask how the compositions are chosen for constructing the 3D convex hull, since there are much more possible compositions than in the 2D convex hull.
Okay, let me explain it on this using this slide. Actually, we used all composition. It was a variable composition search, no specs, and we used composition starting from let's say with the range of each atom from 1 to about 30 atoms. So all compositions were studied with one element, with 0 carbon atoms, 1 carbon, 2 carbons, up to maybe 30 carbon atoms. And in addition, we also studied a lot of we did a lot of evolutionary researches with groups like CH3 group combined with sulfur and hydrogen, or CH3 combined with SH2 group and hydrogen, and all possible combination with a number of groups, let's say from 1 to 24.
Okay, another question from Daniel. Daniel, maybe I missed, okay, but how did you calculate the Liashberg function using which code?
I used quantum espresso. In all cases, quantum espresso has been used.
Okay. What higher and lower hydrogen content means at the diamond anvil cell? for when obtaining different La lanthanum yttrium hydrogen structure. You can, I think, read the.
Okay, let me try to read it.
Yes.
Oh, I cannot find. I just I think I can. Oh yes, I can. Так. Okay, let me. It's better. It will be better. Yeah, if you will read. Read ahead. So let me explain what is the maximum concentration of hydrogen, content of hydrogen can be obtained on the diamond analysis. At this moment, the maximum is barium dodecahydride. So the ratio between metal and hydrogen is 1:12. In principle, it's possible to achieve up to 27 ratio, up to 27. There is a paper about the iodine superhydrides. We've contained about 27 atoms of hydrogen per one atom of iodine. So quite high content can be reached, can be achieved.
Okay, what is driving force to have high temperature for metals, metal hydrides compared to conventional superconductors? And how about the situation in ternary systems?
The hydrides, the main component, the main part of the hydrides, it's a hydrogen. Yeah, and the hydrogen has extremely high Debye frequency. So if you remember the formula of Allendines or Macmillan, the TC directly depends, linearly depends on exactly the Debye frequency, and the Debye frequency depends on mass of atom. So lower mass of atom, higher TC. So the hydrogen is the best material for high temperature superconductor, and this is the best material for superconductivity at all. At least in classical mechanism.
The next question is also related about this question. He asked, you showed some metal hydrides superconductors, so superconducting channels are through hydrogen. I think the metal distance is too far from each other. So what is the role of metal atoms in the metal hydride superconductors?
The main role, okay, I will explain using this scheme. Main role is the electron transfer, of course. The hydrogen itself is a semiconductor, even compressed to above 2 million of atmosphere, 3 million of atmosphere. It's a semiconductor or very bad metal. In order to make it better metal and increase the density of states at the Fermi level, which is very important for superconductivity because the coupling is exactly concentrated and allocated close in the key spaces, close to Fermi energy. So we need to give more electrons and increase the density of states at the Fermi level. And it's exactly because of metal sublattice. So electrons from metal sublattice goes to the hydrogen sublattice to increase density of state in the hydrogen, and hydrogen becomes a good metal and good superconductor too.
Last question from Gilles. In carbon, sulfur, hydrogen, metastable kinetically stable compounds may exist too, but evolutionary algorithms search for thermodynamically stable compositions. How to look for metastable compositions?
Unfortunately, I do not have answer to this question because organic compounds cannot be predicted by USPECs. There are millions of organic compounds. They all are metastable. They all live in real life. We can buy liters, kilograms of such organic compounds, but they are not on the convex hull. They are very far and even cannot be probably predict and construct by using USPECs, unfortunately. Okay. So it's like luck. We found the structure, and this is very universal. We can replace the polymeric chains by any other polymeric chains, and we can replace layered hydrogen by any other inorganic layered also material like tungsten disulfide, molybdenum diselenide, and so on, and graphene. But there is no universal way to predict such structure. So it's just luck.
Okay, thank you very much. It was brilliant. Thank you so much. Okay, so this was the last day of our workshop, and I think lectures are finished. In the afternoon, we have several tutorials, and at the end, we have closing remark and answering question by Artem Oganov for those people who have some questions to Artem. So thanks to all of our speakers today. We will start our tutorial session at 2:45 in the afternoon PM. Okay, thank you. Bye-bye. Shall we start?
Yes, please. It's time to start our next tutorial by Zahed Alahiri on multi-objective optimization. Zahed.
Okay. Okay, before starting the tutorial session, I would like to very briefly show some slides about this multi-objective optimization and how it is implemented in USPACH. So do you see my screen?
Yes.
Okay, wait a minute. Okay, so first I need to say what is single objective and multi-objective optimization. Probably you already know, just to clarify. When we are talking about single objective optimization, we are optimizing only one objective. In USPACH, it means only one properties. When we are talking about multi-objective optimization, we would like to optimize more than one objective, more than one properties. It can be 2, 3, or more. In USPACH, we don't recommend more than 3 objectives. I will tell why in a few slides. But let me give an example. I told you that multi-objective optimization is very important because we usually in the real world, we would like to find solution for problems which with regard to different objectives and properties. So in single objective optimization, for example, one example is that if we want to buy a car and the only important thing for us is the speed of the car. So there is no other preferences and nothing more. Only the speed of the car is important for us. So we find the highest speed car and we buy it. So it's like we are optimizing cars by regarding to the speed. So probably we go and buy a Bugatti. But sometimes we would like to buy a car which are fast and luxury, or fast and less expensive. These are a little bit different because in the second example, high speed car and luxury cars, these being high speed and luxury, these two properties are, these two objectives, let's say, are kind of correlated. So it's like we have still one objective optimization, single objective optimization, because usually high speed cars are luxury. So, but still there are some situations that some luxury cars are not, doesn't have high speed than some less luxury cars. So still it's a double objective optimization. But sometimes these objectives are not correlated, but they are conflicting. For example, we would like to buy a high-speed car, but we don't want to spend too much money. So less expensive high-speed cars is this kind of example. Because usually high-speed cars are expensive, but we don't want to spend so much money. So we need to find a trade-off, some balance between these two objectives. So for solving such problems, we need to use the concept of domination. So I will explain what is domination, because all the Pareto front and multi-objective optimization based on Pareto front is based on this domination concept. So we say a solution A dominates solution B in the whole population if A is at least as good as B in every dimension. It means in every objectives, and better than B at least in one objective. So as good as B in every dimension and at least in one dimension better than B. Then it means A dominates B. For example, look at here. If we are minimizing X and Y, so this is a minimization and not maximization. Red dominates green because it is better than green in both X and Y objectives or properties, because we are minimizing and it has less value of X and Y than green in both of these objectives. The same applies to yellow. Yellow also dominates green, but yellow does not dominate red, and red does not dominate yellow, because yellow is better than red in X, but red is better than yellow in Y. So red and yellow are non-dominated solutions. They are not dominated by any other solutions, but green is a dominated solution. So Pareto front is a set of non-dominated solutions. So here, this is a Pareto front because all these solutions are non-dominated, but all of these solutions are dominated. So here is the mathematical expression. I'm not going to go through that, only concept. So here, when we have two objectives, we will have one line as a Pareto front. But if we have three objectives, we will have a plane as a Pareto front. So you can see that if we increase the dimensionality of objectives, many more solutions will come to the first Pareto front, and therefore we will have many good solutions, or better to say many best solutions. And thus, if number of these solutions on the Pareto front increases, let's say to some extent, then it's like we are doing random search. It's not kind of evolutionary search anymore, because it is evolutionary search, but we have a lot of structures on the first Pareto front, and they are very different. Some of them are good in objective Y, some of them are good in objective ZY, some of them are good in objective XY, I don't know, some are good in X only, and so on. And therefore, we will have a lot of many different objectives and many different best objectives, and this will reduce the efficiency of the algorithm and search. That is the reason that we recommend not to go more than 3 objectives in USPEC, because the multi-objective optimization method which is implemented in USPEC is kind of the simplest one. It's very efficiently works for 2 objectives. It's good for 3 objectives, but not for more than that. So what is implemented in USPEC is simply what I'm going to show you here. So we have this set of solutions for 2 objectives. Here is just some figure. It's not related to material science, but anyway. So the best solutions, non-dominated solutions, are these solutions in red. So this is the first Pareto front. And we will give the first rank to all of these solutions on the first Pareto front. And there is no preference to any solutions between any solutions on the first Pareto front. So both of them are, for example, these 2 are as good as each other in ranking. And then we remove the first Pareto front, and again find the first pair to front for the rest of the population, and we assign the second rank to it. So this is the second pair to front, and again third pair to front, and so on, until we classify all the solutions, all the structures, let's say, in different pair to fronts. There are also other methods, but as I told you, we prefer to be simple. But I think in future we will implement this one too. That's what why I'm showing to you. So in the second method, again, we need to find a pair to front, and in this method, we assign rank based on the number of solutions that dominate that target solution. So because all the solutions on the first pair to front are non-dominated solutions, the highest rank, or here rank 0, is given to all the solutions on the first pair to front. So again, there is no none of these solutions are preferred on each other. So all of them have the same pair to front, same ranking, sorry. But in the second pair to front, if we want to say, it's not like in the first pair to front, it's based on number of solutions that dominate that solution. For example, rank 1 is given to those solutions that are dominated only by one solution. So this yellow is only dominated by this one. This one, this green solution, is only dominated by these two solutions. So it gets the second rank. And this one is dominated by 3 solutions, so it gets the third rank. So ranking in the second pair to front is different. So solutions on the second pair to front may have different ranks. And this can be more useful, especially for 3 objectives. So in USPECH, it is easy to activate the multi-objective optimization. It's just like before you had single objective optimization, so you had to choose only one properties. Here maybe enthalpy, maybe I don't know, hardness, maybe ZT, whatever. But here we will define more than one properties. So in this example, which is for 2 properties, we are minimizing enthalpy and maximizing ZT. And here we are maximizing hardness, minimizing enthalpy, and also minimizing the electric constant. I need to mention, if you have 2 properties here, and none of these 2 properties is enthalpy, Aspects will add the third or fourth, I don't know, properties by default, which is enthalpy, because we always optimize enthalpy in multi-objective optimization. This is important usually because you want realistic materials. So if you here, for example, specify 14 and 3, it's actually 14, 3, and 1. And there is another thing here which I need to mention, and this number in the bracket is some additional feature. It means that until generation number 10, only optimize enthalpy, and after that start multi-objective optimization of enthalpy and ZT. This is useful because it helps algorithm to generate reliable enough structures considering the energy. So we will have a lot of very low energy structures in the pool, and then we change to multi-objective optimization. So this filter helps us to make sure that we will have quite low energy enough structures, which are also good in the other property. And at the end, one of the pictures, the picture that multi-objective optimization will give you is something like this. And you can see pair to fronts in the space of, I don't know, for example, 2 properties that you need, hardness and energy here, or ZT and energy here. And if you are optimizing 3 properties, you will get 3 of these pictures. One for example, hardness and energy, one for hardness, for example, ZT, one for example, energy ZT. Okay, this was just a brief explanation of multi-objective optimization. And let's go to the examples. I think you already got the handout, right? I think Vova shared.
Yes, I uploaded them.
Okay. So let's go to our supercomputer. Okay, I made already a folder called workshop, and I will do everything here. I recommend you do the same thing. Okay, so at first, I'm going to show you the example of USPER for multi-objective optimization, which is example number 34, but we are not going to run it. It's better to make a new example by ourselves, which is even easier to start the calculation and maybe see the results faster. So at first I will show the input file, and we will go through the input, and then we will go and make a new input file for ourselves to make a new multi-objective optimization of hardness and energy. And until calculations are running, while calculations are running, I will show you the results of our multi-objective optimization, which we already have in USPER. I will show you the results and import them files so you can understand how to analyze your results. So first, let's bring, first we need to load USPER module if you are in the supercomputer. Okay. Python 3. Okay. I will make a folder for example number 34. I will go in this folder and copy example number 34 here. Okay, example number 34 is Pareto optimization of figure of merit, ZT, and enthalpy for bismuth telluride. It's a variable composition using VASP, and in the last step, we will do bootstrap calculation to find the ZT. This is useful to check the input file because it helps you also to understand if you want later to do calculation on ZT. So I think you already know many of these keywords because it's the last day of workshop, and even if you had no idea what is USPER, during these 3 days you understood most of the important keywords. So I will just go line by line very quickly. So calculation method is USPER. Calculation type is 301, which means bulk, non-molecular, and variable composition. Autofrac means that automatically change the fraction of variational operators after the first generation. So those variational operators which perform better will given a higher fraction to generate the structures. So symmetries is just which symmetry to choose. Optimization type, you see here we have 2 properties. 14 is for ZT and 1 is for enthalpy. If you want to know what is for what, you just need to check the manual. Everything is written in the manual. And I will just show here. Okay. So in the manual, you can see that 1 is for minimization of enthalpy and 14 is for ZT. Okay. And atom types here are bismuth and telluride. Non-spacious is a block 1001. It means the whole range between pure bismuth to pure telluride, every composition. And population size, number of structures in each generation, initial population size, number of structures in the first generation, number of generations. Stop crit means that for how many generations, if this is a variable composition. So stop crit slightly differs from fixed compositions. Here, stop crit means that if for 20 generations, the best solutions on the convex hull didn't change, just ignore that best solution to be selected as a parent. You will have it in the population, but you will not use it as a parent anymore, because apparently maybe that best solution will be chosen as a parent several times and make similar structures to itself. So you want to go to other direction of other places and regions of potential energy surface. So you don't want to stock. So after 20 generation, Uzbek will not choose those structures on the convex hull if they are there for 20 generation. And Uzbek will not choose them as a parent anymore, but they still exist in the pool. So these are for variational composition. So first gen max means how many different compositions to generate in the first generation, and min atom means what is the minimum number of atoms in the cell. Max atom means what is the maximum number of atoms in the cell. So Uzbek will generate different structures in which number of atoms are between min atom and max atom. And variational operators, you already know, heredity, random, and different type of mutations, which here we have the percentage of them. So 20% by heredity, 20% by random symmetry, because here we have 10% random topology, and then lattice mutation 10%, transmutation 20%, and atoms mutation 20%. So these are keywords for bootstrap. So this is the maximum temperature. These are the steps. Temperature, I mean, it goes every 50 temperature. This is the step. And to be honest, we need to check the manual for it. Everything for this is written in the manual, and I didn't check it. Okay, let's check this later because it is in the manual. We just need to read it together. And here we have ab initio code. So we have 1, 2, 3, 4, 5, 6, 7 steps. 6 of them are using VASP, and the last step is for calculation of ZT using bootstrap. So number 14 for ab initio code corresponds to bootstrap. You can find it in the manual. And these parentheses means symmetrization. So for 4 steps, we'll do VASP calculation and relax the structure. And then when we got the very good relaxed structure, we will symmetrize it for this example, because it helps us to get more reliable ZT. So after this symmetrization, again, we relax it a little bit, and then we calculate the ZT. So this parenthesis only means symmetrization. So if you can do it also like this. So you do 4-step calculation or 5-step calculation of VASP, and then symmetrization, and then calculation of the property. So starting the parentheses means symmetrization. And then here is the key resolution for different steps and how to run the code, which cluster here determines submitting job locally, number of parallel calculations, how many USPECH job, VASP job to be submitted in parallel, external pressure is 0, and these are options for restarting USPECH. So if this is 1, this means we will restart. If this is 0, it means we will not restart. But if we want to restart, we need to mention from which generation we would like to restart. For example, this is a little bit different from restarting from the point that USPECH is crashed or is stopped. This is starting from some special point, some certain point. So for example, you calculated some system using USPECH for 15 generation, and then you understand that probably after generation number 11, USPECH calculation is going wrong or is stopped, or for some reason your MATLAB files are destroyed or removed or doesn't work anymore. So you would like to start from some earlier generations. So we can write here, start from generation number 11. And here you need to say, take the result from which result folder, because we have result folder 1 by default. But if you run the calculation again, a new calculation in the same directory, USPECH will generate result folder 2 and result folder 3 and result folder 4 and so on. So you need to specify, for example, take the results from result folder 3 and from generation 11 start. Okay. These are about the input files, which I think you knew already, most of them. The most important thing here was optimization type. And I already told you, if you write here 5, for example, until generation 5, it will only optimize enthalpy. It's like searching for lowest energy structures. And then after that, it starts multi-objective optimization of energy and ZT. So if there is any question here, you can ask now, and then I will go to the, I will continue. Okay, let me look at that. How long will we have access to the accounts we are given? Well, I think Vova should answer that. I don't know. Can we still go on later today or tomorrow? I think you will have it for a couple of days, but I'm not sure. Let's, Vova, do you know the answer of this question? Okay, I think he will answer you shortly. Okay, guys, now let's make a new calculation for ourselves. Let's make a new input file and make a new calculation. So let's copy example number 1. First, we need to make a folder for it. We go to the folder and copy example number 1. This example is generally for calculation, vast calculation of silicon, finding the lowest energy structures of silicon with fixed composition. Let's look at the input file and change it. So calculation type is USPECH, okay. Sorry, calculation methods. Calculation type here is fixed composition, non-molecular calculation for bulk crystals, but we would like to find variable. Okay, no. Wait a minute. Okay, I made a mistake in the handout. I changed this to 301, but this needs to be 300. I will explain why. Because I will explain shortly. Okay. Then we have op type. We would like to optimize enthalpy and hardness. So let's have two properties. And instead of silicon, let's calculate carbon. And here num species is 8, but we would like to make it 1 because it is variable composition. Although we wrote here 300, I will tell you why it is variable composition. So let's make this 1. And okay, let me tell you now why. When we have a kind of fixed composition, for example, here, we can add some two keywords to make it variable composition. But this variable composition is just like increasing number of blocks and not changing number of atoms. For example, I will tell you better in this example. For example, let's see, let's say we have silicon and carbon, and we have 1 silicon and 2 carbon. Okay, if we write it like this, from the beginning to the end of Usbach calculation, all the structures will be generated by 1 silicon and 2 carbon in the unit cell. Okay, but if we add these two keywords, min add and max add, which means minimum atom and maximum atom, it will not be like before. For example, we will make minimum atom in the unit cell is 2 and maximum atom in the unit cell is 8. Okay, this is kind of variable composition. It is fixed composition. I mean variable number of atoms in the unit cell. Okay, so in this case, Usbach will not generate only 1 silicon and 2 carbon for us. It will generate once 1 silicon 2 carbon, once 2 silicon 4 carbon, once 3 silicon and 6 carbon. But if it is 9, because 3 silicons and 6 carbon becomes 9 atoms in the unit cell. If it is 8, it will not generate that. So I think you understood that. So if here we are looking for carbon structures, if we write here 1 species and minimum and maximum number of atoms from 2 to 8, it means that Usbach will generate for you structures with 2 to 8 atoms in the unit cell. It is fixed composition, but different variable number of atoms in the unit cell. Okay, so we need to add these two. So population size is 20. Let's keep it as it is. Initial population size is 30. We can keep it as it is. I don't mind even changing it to 22, but as you wish. Let's keep it 30. Number of generation is 25. I will make it 15 for myself. And stop create means that for this, because this is not variable composition by this keyword. This is 300, which means fixed composition. So here, you see here, we don't have a convex hull. So here, stop create means until 8th generation, if the best structure didn't change, stop the calculation. So let's keep it as it is. And best fraction means how many fraction of atom structures are allowed to be selected as parent and generate new structures. Reopt all means do we need to reoptimize old structures in previous generations? No, we don't need it. And here are variational operators, percentage of them. Let's keep it as it is. Okay, we here have 6 steps of VASP calculation, and here we have the k-point resolutions for each of these steps, how to run VASP. Okay, we will going to run it on the cluster, on the supercomputer by one. So we need to also change the job for that. And let's make 20 or 10 non-parallel calculations under zero pressure. So I think the input is ready. Another thing which you need to do is you need to bring here the podcar for carbon, because we are not calculating silicon anymore. We are calculating carbon. I mentioned in the handout that you can find the podcar for carbon in this directory, temp aspects workshop podcar of carbon. So we just need to copy it in the specific folder. So it's done. And then we need to change the submission file. Submit job local. The only things that we need to change if you are doing this calculation in our supercomputer is to change number of cores. For VASP, it's better to use more number of cores. Let's make it 4 for now, and everything else is ready. By the way, in the bootstrap example, if you decided to run it in your computer, our computer, whatever, you need to also mention module load bootstrap if you install it as a module. Okay, so the only things that we changed was number of cores. Let's save and exit. Okay, so for running, we will use some job file, which again I mentioned you can find it in this directory, temp aspects workshop job.sh. Let's copy it here. Okay, so here we are running aspects, and then the scripts will sleep for 150 seconds, and again will run. Okay, there is, yeah, and again it will run the same script will run itself if USBEC is not finished. Okay, so I think we can run it using spash job.sh. Okay, I think my job is in the queue. Now it's running. We can check the log file. You see composition 7, 5, 7, 8, 2, 8, 5. These are different number of atoms that USBEC will are generating in the unit cell. So different number of atoms because we added minimum atom and maximum atom. Okay. Okay, so just to check one of them in the calc fold 1, here is the postcard. It has 8 atoms and it just started calculating it. And here is the incar. I didn't explain anything about the VASP input files because it's not for this workshop. I'm sure you know, many of you know about that. And anyway, you can find the examples of VASP input files in specific folders of all the examples of USBEC. Okay, so we can run it, and I don't know, you can for yourself look at the results later when it was finished. But I will show the results that we already have for multi-objective optimization of energy and ZT. Okay, because we have already calculated this example and we have a reference folder for that. For showing the result, I will go to my own laptop to Specs Workshop. Here we have example number 34. The reference folder. Okay. There are 3 files for multi-objective optimization in this folder, in which 2 of them are important. One is Pareto ranking, and second is one PDF file, which I will show you. Okay. In multi-objective optimization, you need to use this file instead of best individual, because in multi-objective optimization, best individuals are determined based on the Pareto ranking of the Pareto fronts. So here in this file, you can see number of the ranking of Pareto fronts. For example, all these structures are on the first Pareto front, as I mentioned in my slide. So this structure, they are probably very different, but all of them are the best solutions for us. Okay. And then second Pareto front, third Pareto front, fourth Pareto front, fifth Pareto front, and so on. So here is the ID, origin, how this structure is generated, the composition of the structure, enthalpy, volume, density, and here, and can't see it. Let's make it like this. Okay. Okay, here is ZT value, which is calculated using bootstrap for each of these structures, and energy above convex hull as a fitness for energy. So we are minimizing this energy and maximizing this ZT value. Okay, and symmetry, K points, and here some orders, which is not important for us. Okay, so let me show you the first Pareto front. The first Pareto front contains which structures? Non-dominated structures. These in these non-dominated structures, we have always one structure which is the best in one property, and then we have structures which are good in both properties. So this structure, the first one, you see it has really high energy above convex hull, but because of the high ZT that we found for this structure, it came to the first Pareto front. Let me show you also the second file at the same time, so you can visualize what I'm talking about. So here, energy and thermoelectric constant Pareto front file. Okay, so that's the structure which I talked about is here. So it has a huge ZT, but it has a low, also high energy above convex hull. And then we have also one structure on the first Pareto front, which has the lowest convex hull and lowest ZT among all structures on the first Pareto front. So as Artem mentioned in his slides in the first day of the workshop, one of the advantage and one of the useful things that multi-objective optimization brings for us is that we can just discard all those crazy results that we have because we are optimizing two objectives. For example, you know that ZT1 is very good. ZT can go until maybe 2, but generally many of these values for ZT are just crazy. It's crappy. It's not good. So we will have, if we wanted to optimize ZT, if we didn't have multi-objective optimization, this structure here, which is a crazy bad structure, unrealistic structure, would lead, and then this structure and this structure, and only these structures would get a chance to generate new structures for the next generation. So you could imagine your spec calculation would go to the very wrong direction. But right now, when we have multi-objective optimization, this structure here, which is actually the best structure because it is on the convex hull and it has a very reasonable ZT, this also have a chance as this one to generate, to be selected as a parent and produce and create a new child using variational operators for the next generations. So, and these structures on the first part front are these that you can see here on the black line. So these are two important files for multi-objective optimization. And I don't know if I need to tell about other files or not. I will probably very briefly explain because you already know all of them. You probably heard about all of them and in other tutorials. But important files here are one, extended convex hull. So here you have structures based on which are ordered based on their energy above convex hull. So we got 4 structures on the convex hull. 2 of them are pure, so only beryllium and only titanium, and we have also some structures on the convex hull from the combination of these 2 elements. And this structure here, sorry, bismuth telluride, we are talking about bismuth telluride. So this structure here, bismuth 2 telluride 3, is also known in the experiment, and this is the structure I suppose that we got here in the Pareto ranking. Let's check, because yes, you see it is bismuth 2 telluride 6, the same structure, which is known in the experiment. It has a very high good ZT and it is stable. So spec found it just successfully. So here I showed you that we have structures based on the order of their energy above convex hull, and then we have the same file for the postcards of these structures. So if we want to check this bismuth telluride, the experimentally known high ZT structure of bismuth telluride, I can just create the VASP. I can show it to you using Vesta. This is the structure. Let's make X1, X2, X2. Okay. So this is the structure that you can see. Okay. Okay, another important file is individual. You will get the same information as we had in the Pareto ranking file, with one difference here. There is no order between the structures. The first structure which got converged and the relaxation and bootstrap calculation was finished for it was written first to this file, and then the second, and then the third, and so on. So basically in this calculation, we had 40 generations and we optimized 4,563 structures. But in the Pareto ranking, we will have ranking of these structures and then the same information of each structure. And you can find postcards of all the structures in the gathered postcard file. The order of these structures is according to the individual file. So the first individual structure here is also the first in this file. And then we have the convex hull file, which very quickly you can check and see which structures and how many structures are on the convex hull. And we can also check the convex hull picture. So you see, we have these two structures on the convex hull and some new some structures close to convex hull. And this is the place for bismuth telluride. Okay, I will also show you here. This is the file that will show you, if you remember, I told you that we have here in the input file an auto-frac keyword, which change the fraction of variational operators according to their performance. So if, for example, heredity makes better child for the next generation, in the next generation, because we will have this information, algorithm automatically will give more fraction and more portion for generating structures to heredity, for example. And you can just track here how your variational operators work in generating better structures. So in this calculation, soft mutation was the best variational operators overall. And I think, okay, this is energy and volume figure. This is energy in different steps. I will tell a few things about this because this is important. Sometimes people do not know if they are doing Uzbek calculations, with enough steps for each structures. So for understanding if you have enough steps, it means you need to have enough step to your so your structure become fully converged and relaxed. And to understand that, you can check this file. So if we have E1 corresponds to the energy of the first step of VASP calculation, E2 is corresponds to the second VASP calculation of a structure, and so on. So here we had 6 steps. We have 6 energy for each structure. We had 6 steps of VASP calculation for each structure. So you can see that energy of first step and second step are not very well correlated. Second step and third step are not very well correlated. Third step and fourth step are becoming correlated. So far it means 4 steps are not enough because you are not converged. But from the when you go to the fifth step, you see that fifth step and fourth step, the energies are very well correlated. So I think 5 steps should be enough for this calculation. We have here also for 6th step, which is even more than enough. The 7th step is for bootstrap. So it's not vast calculation. We only took the energy from previous generation. So this is energy from 6 and energy from 6, basically. Okay. I think I'm finished by showing the important files. Yes, if there is any questions, please feel free to ask. Let me check. Okay. Here's if the stop criteria for the variable composition simulation is only the stop criteria for a specific composition, how do you how do the simulations know when to stop? In the variable composition, stop grid will not stop the calculation. Only, you know, generally there are 3 ways to stop USBEC calculation. One is by hand, just stopping it. Second is by number of generation, and third is by a stop grid. But in the case of variable composition, you will not have stop grid for stopping USBEC calculation, so only number of generations will stop the calculation. Incremental Monday, okay. I think after completing, why I have no pair to ranking file in the reference? You should have it, I don't know. You should have it. If it is only you, that's strange because you're using the same in a USBEC and the same reference folder. Which example did you take? The first example which I showed the input file and now I'm showing the results is example number 34. But the example that I took and we changed together the input file and we ran it, it was example number 1. The reference file as instructed. Okay. I think there is no more question. If you have, please don't be shy. What is actually checked by the which files are read? So for our example, we changed something in submission folder, job, submit job, local, because we are locally run the structures. So what we changed here, we only changed.
Zahed, sorry to interrupt you, but could you please read this question out loud, because on the YouTube translation, the chat is not saved.
Okay. Daniel asked me, in the case of vast calculation, what is actually checked by the check status script? Okay, which files are read? Okay, so the question, I didn't get it wrong. So by check status script, USBEC basically checks if the job is still running or pending, or the job has done, calculation is finished. So if it is still running, or I don't know, it's still in the queue, USBEC will do nothing about that. But if it is finished, USBEC will go and take the results of that calculation. Right. And which files are read? USBEC will not read any file. We'll read the output of some commands like skew, for example. Okay, I'm on my laptop. Yes, like skew to see the job is there or not. This is maybe too general question, but do you think that IRBO, actually I don't know what is it, or RIBO potentials available in lamps are good enough to predict carbon structures? I didn't work with lamps actually. I can't answer this question. If such a question is here, I think he knows better. Okay. Hi, Zed. Must we have bootstrap pre-installed in the cluster? It is installed already. I didn't test it, but it is installed. If you want to run this example number 34, you need to load bootstrap using what I'm writing here. Module load bootstrap, and then you press tab and you will find it. Okay, you need some dependencies. You need to also load these dependencies like this one and this one. So like this, I will put this in the chat. So for those people who want to know it. Okay. What the hell is that? Okay. Sorry. This is not the right command which I wanted to share. This is the one. Oh, okay. It was not for me. Did you, Carlo, did you load? This is technical problem running them on my local Linux. Seems related to Python 3. So you need to first make sure that the Python modules, which is required by USPEC, is installed. Basically, you have some problem with random topology, and for that you need to make sure that you have SciPy and NumPy. If they are there, you shouldn't have problem. Then I don't know, let's try to run it. Okay, you know, there might be two things to check. I will check one of them because that's my duty, and that is because this random topology is a binary file, compiled file. It is compiled by Python 3.6. Maybe, I don't know, that would cause problem.
I have a comment from Pavel Bushlanov. He just wrote to our Telegram chat that these comments, module load comments, should be included in submit job files.
Which module?
Glad that you.
Bootstrap? You mean for what? Let me check. I mean, okay, wait a minute. Okay, this I already mentioned, that people need to, in their submit job, if they want to run Bootstrap, they need to add this line which I wrote in the chat to their submit job local. But the problem with which Carlo raised, I was talking about that. So I would suggest you to try to, I don't know, probably run USPACH using Python 3.6. Maybe that solves the problem, but I will check 3.7 and 3.8 and other things to make sure that will work fine. If we need to compile a new file for those, I will do that. I mean, for random topology.
Zahed, we're a
Yes.
little short of time right now, so maybe
I will answer in the chat. Yes.
yes, and maybe if it's okay for Hubert to start a little later. Hubert, are you here?
I'm here.
So is it critical for you to start right now, or we can take another 5 minutes?
Absolutely not. I have 5 minutes.
Okay, thank you.
Thank you. Thank you, everyone.
Okay, dear friends, I think we can move on to the next tutorial given by Hubert Okadome Valencia from Japan, from Nagoya University. And he will present his own software, which visualizes the results of USPECs with interface with WASP. Hubert?
Okay, is it okay? Can you hear me?
Yes, everything is fine. We can see your presentation and you also.
Because I had a little trouble, technical trouble, actually a big technical problem.
Really?
So today gonna be a little rock and roll. So
Okay.
in this tutorial, I will introduce you the GD's visualization software for USPECs and VASP. So this software originated from Andrew Roll in Curtin University in Perth, in Australia, and me and Gilles Frapper had our grain of salt in order to introduce USPECs and VASP to this nice visualization software. So I'm gonna give you a direction to install JDs, but maybe I can make that available with. I'm gonna give that to Vladimir, and he will share the document because it's not really So interesting. So for now, just we didn't release yet because we are waiting for publication to arrive. So it's still a pre-release version, but at the end, maybe it's going to be little different command to download and get GDs. And I didn't know there was a 10.4 version. Sorry, Vladimir, maybe I mistake your announcement or something. So I'm going to talk mostly of 10.3, but I think there should not be so much difference anyway.
Yeah.
So, so I did a support video which I share on YouTube. So if you have a phone, you can take a picture of this. It's going to bring you to this YouTube video. And it's a little fast video, so there is a few advantage compared to that, is that you can pause and you can mute my voice. And I suggest you to read the subtitle and go very slowly because it's kind of a little fast, and you can get nice, relaxed self-teaching at home. So I'm not going to launch it actually. So let's see. So I'm going to install pretend install because of course I install it. So I'm going to make a directory and this command I will get you from Vladimir. I think he will share on the maybe website of the school. I don't know how you're going to do it.
Sorry, Hubert. Which one? What exactly should I share? The address?
Slides. If possible.
The slides?
Yeah.
Actually, I don't have them. Maybe I should ask Alisa. You sent her your presentation, right?
I didn't send them because I had a little trouble. That's why you don't have them yet. So I'm going to send you after this tutorial.
Okay, and I will share them, of course, yes.
Okay, thank you. So this is, it's kind of not so difficult to install GDs. Just follow the instructions. There is this little trouble of pre-release version. This one is not necessary actually. So I'm gonna pretend installing. Actually, it's gonna install all that stuff. So there is requirement is GTK, but it's actually very easy requirement. So unless you have a Windows version in which we have no support, there should be no so big problem. So when this step is over, so actually you can see GDs are lots of different formats, and we just add the specs and those things. So, I'm going to interrupt that because it's a little long. So when you I'm going to do it a little faster. Sorry. So when you finish installing, by default, it's going to put the executable into the binary directory, but you are free to put it everywhere you need. And so it's done. So in this directory, you're going to have GDs. Actually, it doesn't look like this, but I remove Windows decoration. Otherwise, it's not so interesting to have many different versions. So what you can do is, as I said, you can look at some examples that are provided by GDs. So as you can see, it's a kind of quick to load lots of molecules, even complicated one. There is no big deal. It's extremely fast visualization. This is why we choose it actually. And so the new things is maybe you get more interested in is so in your USPEX installation, you have application examples. So you can take one example and display it. It's going to show you. I'm going to explain later. But why only one? You can take all of them at the same time and display all of them at the same time. So it's a little longer, but you see, it's not that long to load all the. This is all the example of specs. -1, it's transition path sampling, because it's because of me. I still didn't put transition path sampling because I'm not familiar with the format. It's kind of a new format. And I don't know, have you talked about transition path sampling in this school yet? Maybe not. Okay, so anyway, I'm going to create another directory. And today I want to show you something which is a little more easy, because you have lots of no experience in USPEX, all of you. So I can do a little more complicated things. And let's do it more simply. I'm going to create a new model. And on that new model, I'm going to launch a USPEX calculation. So you know already what is 300. So I want a variable composition. And I'm going to use silicon carbon as example. Why not? So I'm going to add carbon. And this is the num species which was described, I think, yesterday or the day before yesterday in a variable composition tutorial. So it's pretty much what you already know. And the nice thing is, when you don't know a parameter, you can stop, and it's going to show you the name of the parameter and the chapter of the manual in which you should look in order to have more information. Because I give only 2 lines of information, but in the manual, of course, you have a more clear definition. So let's not forget optimization type. So I'm going to put some parameter for population. It is, I made it up. It's not so serious calculation. So actually, this is variable composition. So you have to, it's mandatory to enter minimum and maximum composition. So we have silicon carbon. We're going to do from 2 to 8 atoms in a lattice. And calculation is the most important. I'm going to change the name of the model. Calculation is the most important of the tabs, because this is where you're going to define. And I add a very nice feature, which is called auto step. So auto step can actually make it for you to fill the input of VASP or the input and option of gulp. It's going to do that automatically. So we're going to do 3 steps of gulp calculation. And so you have to enter. So this is a library that is provided with gulp. So if you don't have gulp, I strongly recommend that you download it at Curtin universities. It's free for academic use, but you have to register your address. Maybe I'm going to give you the address in the chat. So once you do that, you can select pseudo potential from the one available. So I'm going to select a tensor of pseudo potential, and here So I always do timeout because sometimes when command is stuck, I don't like USPEX doesn't kill it. So I prefer to kill it myself. And this is a standard GURP calculation. So there is no trap in there. So you need to repeat this step for all the steps. So step 2, another GURP calculation. Where is it? Library. We're gonna select another tensor. Of course, you can change also the pseudo potential. You can go from Ruth pseudo potential to more clever pseudo potential. Okay, and finally, third step. So third step is another GURP thing. So if you select VASP pseudo potential, when you have VASP, you're going to download the database of pseudo potential, and you're going to extract it somewhere. You can also open this database of pseudo potential, and GD is going to make your pseudo potential file by himself. So you're going to assemblate everything. Okay, so this is the last step. So let's check. I mistake one step. Yeah, I mistake one step. So I'm gonna redo it. Sorry, I don't know. As I said, I had some trouble this afternoon. So maybe I hope it's gonna work well. In any case, you can. I invite you to see the YouTube video, which I hopefully did before trouble happened. I don't know why I have to do that. And third one, and hopefully this should be okay. Okay, when all steps are the same, all you need to do is check a little your parameter for USPEX, and you can save and execute USPEX. And then you see USPEX is running, I hope. And maybe you can see the familiar USPEX output. So this is really USPEX running right now with silicon carbide. And it's the GURP calculations. The GURP calculations are extremely fast. So while this is running, it's going to fill up all the graph on the fly. So you have the whole graph, which is the energy of each structure per generation. Base graph is going to be filled later, is the best candidate found for each generation. And you have the, what's the name? Is a composition graph, which is going to show you the composition also between silicon and carbide as it's running, so little by little. So I'm not gonna let this calculation. It's not that long. You can probably do it, but we have better things to do today. So I'm gonna just show you the result because I did it just before. Which one is that? Yes. It should be that one. Yeah, it's that one. So after you can see I go to 100 steps, which is what Zahed just talked about a few seconds later. So you can put stop critical, but it's a variable composition, so it's not going to stop. So this is my best structure per generation, and this is convex hull. That is fine. So I remind you, and this is Tersov pseudo potential. It's not a really serious calculation, but you can still see you have silicon on, carbon on one side, silicon on the other one, and silicon carbide. So it's look not that stupid. So just finally, I still have 5 minutes, I think. I'm going to show you what to do with that. So you take the final step, and you have, for example, this silicon carbide is the one which is on the convex hull. So when you click on the one structure on the graph, it's loaded in the structure visualization. And what we can do here is we can calculate VASP of that. And for example, this is tensor pseudopotential. So I would like, for example, to have better geometry optimization. So, okay, everyone knows it's semiconducting. Huh? So I'm gonna do medium optimization or geometric optimization. So this one I'm gonna do parallel because we are late. So this one is VASP VASP interface. So in order to launch VASP calculation, so that one I don't need to change. Also, I'm gonna do okay. I'm gonna check a little the electronic structure. Ionic, I'm gonna do conjugate gradient. I don't think there's gonna be more than 20, but should be okay. Podcar interface is funny because, as I said, you load where you unpack all your podcar, you open, and it's gonna create by himself a podcar. You can do some flavor if you want hard pseudo potential. You can apply it. It's no problem. It's working actually quite nicely. And finally, there is I advise you to always check the calculation path. So I'm gonna make a new path. I'm gonna create a folder. It's example. Open, and then it should be safe to save and execute. Hopefully, I hope. And you can see in the task manager that VASP is running. So it's a bad idea to run it with Zoom at the same time. So you recognize probably the VASP output. It's very simple. So when you do the first step of optimization, after the first step of optimization, you're going to start giving a graph, which is energy versus SCF step. It's just a practical thing because if your calculation is going completely crazy, you're going to see it in that graph. It's going to go up the sky. It's very easy to see. So that calculation I did also, so it's not so interesting. We're going to discover that silicon carbide is semiconducting, which is a shock, I think. I think I have it here. Yeah. So what is important, I see Zaid did a few minutes ago. He checked VASP running while doing the spec calculation. You can do that here. You can have the spec calculation and you can open the VASP run .xml. So you can follow both at the same time. You can also see if one calculation is stopped or going crazy, and you can key it in there. So just as a conclusion, I'm going to show you if it doesn't want. So bound on those, we were not density of state. I mistake. So I'd say between -10 and +10, but of course you cannot see anything. So you can see this is even tensor. This is a pretty good semiconducting. I think there is no question about that. So that's gonna conclude my little show off of GDs. And if you have questions, I invite you to ask them in the chat and also on the GDs Git, because that's where problems are also reported. And of course, you can contact me anytime. All right, thank you for your attention. And I'm open for questions. Is it okay?
Thank you, Hubert, for the great presentation. And we're waiting for the slides and
okay.
the link to the YouTube video.
Okay.
But it's not like right now, but
I can give it to you right now.
so I will upload it to our site, and now it is time. Okay, I see some questions in the chat. Yes, there is a question from Busheng Wang.
Yeah. I think I missed. Did you, Vladimir? Did you send an announcement for that 10.4 USPEX version?
Yes, in the mailing for the participants, I sent the link for downloading, but probably I didn't send it to you or and other lecturers. So that was my mistake. But I think the differences are not that big and crucial. The head can comment on that.
I'm gonna look in the next week, and probably maybe if there is not so much things to change, I'm gonna change GD to the next week. No problem. So I give you also the link for Gulp, which I think you use a lot, so you should provide the link to Curtin University, I think at least once. And okay, I'm gonna send you the presentation. Can I do that? PDF, okay? Actually, well, we're gonna discuss that, Vladimir, later.
Okay. So now it's the time for the next tutorial about predicting of nanoparticle structures by Sergey Lepeshkin, my immediate colleague from Skolkovo, his postdoc in Skolkovo in Skoltech. So Sergey, are you ready?
Yes, do you hear me?
Yes, we hear you well.
I should share my screen.
Yeah, please do.
Do you see the screen?
Not yet. I think, Hubert, can you stop your sharing?
It's my fault. Sorry.
No problem.
Okay. Thank you. Sorry.
Sergey,
So, one
you
more.
may try now.
Is it normal now?
Yeah, now we see your screen.
Oh, it's great. So this tutorial is about structure prediction of nanoclusters. And at first, please open tutorial file from conference site. So I also open this file. Workshop materials. Okay. So let's go. At first, you should load all necessary modules. This is Python 3, new version of USPEX, and Gulp. So I will do it with yourself. So module load Python 3. USPEX and Gulp module. As you know, USPEC has a lot of different examples for different systems. So we will find examples for prediction of nanoparticles. Cluster is 0D objects, as you know. So we will type this comment to find examples. USPEX -e grep 0D. And as you can see, there are 3 examples in USPEX with nanoclusters. It is with Lennard-Jones nanoparticle with Gulp, MAPAC, and FHI AIMS. So we choose first one, the simplest examples, Lennard-Jones nanocluster. So we create new folder, for example, example 08. CD into this folder and type command uspex-c 08. So we copy all necessary files from this example. Now we can see these files. So go to the input.txt file and see what is it. As you can see, the first one is calculation method is uspex. Calculation type is 000. First 0 is dimension. So in our case, it is cluster. It is 0D object. So we put it 0. Second 0 is molecular, non-molecular mode, and the second 0, the third 0 is variable composition or fixed composition mode. So then, after frag parameter equals 1, as you know, I think you already know, it means that we use automatic adjustment of variation operators weights on the fly. So the next parameter is op type. It is enthalpy. So we optimize enthalpy or energy of our cluster. The next parameter is atom type. We put it molybdenum. We do it so because the size of this molybdenum atom is approximately equal to the size of atom in our model system in Lennard-Jones cluster. The next parameter is num species. It is number of atoms in our cluster. In this example, it is 36, but we change it to 13. It is more simple calculation just for it. So next parameters is population size, num generation, and stop creep. Usually population size, it is the number of structures in each generation, and it should be approximately 2 times more than the number of atoms in the system. So we put it to 20. Num generations we also change to 20. And stop creep parameter is the number of generations which USPEC calculates when the USPEC calculation stops if it cannot find a better structure or structure with low energy. And it should be approximately equal to the number of atoms in the system. So we put it, we change it to 10. The next section is variation operators. These variation operators are the same as in standard calculation of USPECs. So you see heredity, random operator, and mutational operator. So the next section is ab initio code. We use gulp in this calculation, so it is 3. And the next parameter is very important. It is vacuum size. Vacuum size means empty space that we add to the cluster in each direction. This is needed for calculation clusters in program for periodic bulk materials, such as VASP, quantum espresso, and so on. You should know that it is very important parameter, because if you make this parameter too small, cluster will interact with each other, and the calculation will be inaccurate. But if you make this parameter too large, then the supercell will be very large and the calculation will take a huge time. So you need some compromise in this parameter. But for gulp, it doesn't matter because it is not DFT calculation. So we put it 10 or 12. Then comment executable. So we use gulp for relaxation. And the last section is non-parallel calcs and which cluster. So we change which cluster from 0 to 1. It means that all our gulp calculation will be at computational nodes, not at head node of supercomputer. And non-parallel calcs we change to, for example, 10. It is a parallel calculation of, it is a number of jobs which успех run simultaneously. So I think it is all. And now we are ready to start. Here is it, description of. So now we should run успех, but in this workshop we will run успех also on the computational nodes of supercomputer, not on the head node, because otherwise the supercomputer will fall if 60 people run simultaneously the успех on head node. So we use the following script for this run. You can copy it from here, but I will copy it from this folder. So cp that is all, and now we run the calculations. So it is already started. You can see that it generated 20 structures with random symmetry operator. It tries these symmetries, and actually these 10, the first 10 jobs are already queried to supercomputer. So you should do the same things. But to obtain the results more quickly, I will start this calculation also on the head node. You should not do it, but only for obtaining the results. So I will make another folder. So that is all. And now we will start it on head node. It is just uspeks minus R. And you can see so in this case, both uspeks and gulp calculations are on head node without any query, so it is very fast. And now we will wait a couple of minutes and obtain the results. So for each structure, we have 5 different relaxations with 5 accuracies. So now 20 structures are already calculated, relaxed. So the first generation is done. Now it is second generation. We produce the second generation with variation operators, and now it is calculating. So now the third generation is already done, and I think that it is sufficient to get results. So the results, as you know, are in results folder. And I think we can plot in Vesta the obtained structures. So as you know, the best structures are in good structures file. So if you open it with Vesta, you can see the obtained results. So now we add bonds. And you can see that we obtained regular icosahedron. It is the most energetically favorable structure for Lennard-Jones 13 cluster. Regular icosahedron with the atom in the center of it. So it is very simple example, and after only 3 generations, we obtain the right result. So I can see we can stop this. Now, if you have some questions, please write them. If there are no questions, I will briefly show how to start variable composition calculation for clusters. So in this folder. Oh, there are questions. How do we know the obtained non-cluster is reliable or not? So I think the question is how that non-cluster is the most energetically variable. As you know, there is no guarantee that evolution algorithm gives you the most variable, the state with lowest energy. So approximate criterion is top crit criterion. So for example, if for 10 generations you should not obtain better structure, it can be the most favorable structure. How sensitive are results from the vacuum size? With DFT calculations is the most important case. We know that the optimal vacuum size is approximately 6 angstroms. So you should add in vacuum size the number of 6. So it will be rather fast, and the calculation will be rather accurate. And how sensitive are results? Not sensitive when vacuum size is sufficient. So if, for example, if vacuum size equals 3, 4, it is not accurate results. So, and I think starting with 6, it will be normal results. And you should know that 6 angstroms, it is not the distance between clusters in supercell calculations, because actually each edge some additional, I think, approximately 2 angstroms to the each atom at the surface cluster. So if you make 6 angstrom, actually it will be 8 angstrom between clusters in different cells. So new question, can we use ab initio code Gaussian? Could there be Gaussian? Could there be any point in using instead of Gauss? We have Gaussian, we have interface with USPEX and Gaussian, but as we know, Gaussian is not very, it's quantum chemical program, but the convergence is not very good. So for this purpose, we firstly make calculations with WASP and then recalculate the obtained structures with Gaussian. It will be most robust way to calculate the structures. Why are 5 size of vacuum size, but not 3 in X, Y, Z? 5 size means that at each 5 vacuum sizes means that we have 5 different relaxations for each structure with 5 accuracies. So 10 is for first relaxation and so on. And in XYZ directions, we have equally, the vacuum size is equal. So you should not specify 3. You shouldn't specify vacuum size separately in XYZ directions. So for each step of relaxation, you should specify only one number of vacuum size. You may check this parameter by running test on, I think it is test on single story. When vacuum size increased, total energy should converge to a constant value. Choose the lowest one. Yes, I think it is rather good advice. How we use an ab initio code in input file? Are there different command or what? So you can use ab initio code like in other examples in input file. For example, 3 equals gulp and 1 equals vals, for example. So you should only change ab initio code to 1, 1, 1, 1, 1, 1, and so on. And common executable, you should also change it, but it works only if you run calculations on the head node or on your laptop computer. So if you run calculation on supercomputer in computational nodes, you should change submit job files.
Siroja, if I may, I would like to correct you for this, because what you said was for previous version. Right now, if people choose command executable in the input file, it's also for jobs.
So now command executable is also for running on supercomputer. I understand, yes.
Yes.
Zahid? So as I had said, you can change command executable according to your first principle code.
Yes.
Use Orca code. Yes, by the way, we use Orca code, but it is very complicated to install it on supercomputer. So if you can use. And I will quickly show how to run variable composition calculation. So in this case, you should change variable composition to 1. Now species, for example, you can run calculation from 10 to 15 atoms. So you should type 10 and 15. And I think that's all.
Actually, Sergey, I think it is
We
worth
have no
to
time, yes?
note. Sorry. It is worth to note that the variable composition for clusters is not included in the standard release. So if you need this type of calculation, please contact me or Sergey.
Yes, it isn't the final version of variable composition. So, for example, it has not very important variational operators, add or remove atom. But now I will briefly show you how to run it. So I only, sorry. Actually, I just add transmutation operator and it equals 0 because it is some bug. So I think that is all, and we can run the calculations. So as you can see, it generates structures with all possible compositions from 10 to 15. And the other calculation will be similar. So another questions from the chat. So any other questions?
Okay, everyone, now we have planned a 15 minutes break, and then we have our last tutorial for this, actually the whole conference, and then some closing remarks. So those who want to discuss the tutorials may do it in the chat or here, and see you in 15 minutes.
Yes, the last question, USPECH also support FHIMs? Yes, USPECH supports FHIMs, and you can even find an example with FHIMs code. So I think it is all. Thank you very much.
We will begin with the two-dimensional silicon, which is combined with the USPECH code. So step one, we should activate the environment for all necessary code. Yeah, it's very important, to be honestly. We need to make sure the USPECH version 10.4 is available, the VASP is available. For those lucky one who got access to the OLEC, you may directly using the module load away to get access to it. It's very easy and quick. And for the others, if you are going to do the practice on your local machine, just make sure the USPECH version 10.4 and the VASP is available for you. Then we should create a space folder for the practice and get the examples which is already prepared for you. I assume that you already got them. If not, I may show you if you are on the OLEC, I may show you exactly the location. And for the one who are planning on their local machine, I think I may going to share a link. You may download them. Wait a moment. Yeah, just a second. Link. Okay, if you need it, you may go download it, the hands-on document and the examples from the Google Drive link. But also we may build it after, you know, based on the examples of the Uzbek. So don't worry about that. Let's continue. When we finish the files, example files, let's move on the parameters which related to two-dimensional in the input file. And after the 3 days tutorial, I guess all of you are quite familiar with the definition of the parameters. For example, for the first one, for the calculation type, considering we're going to do the two-dimensional. So for the dimensional, I mean the dimensional one, we're going to use -2 for it. Some people may curious about why not the number 2. The reason is number 2 is already given to the survey system, which is also a 2D system, but on a substrate. So here for two-dimensional silicon, I mean isolated two-dimensional one, we're going to use -2, and molecule, of course, is no. And variable composition, considering we're dealing with the unary system, only silicon. So variable is, of course, is 0. But in fact, the variable composition function is already available since the version 10.3. I will strongly suggest you to have a look, have a try. It's a very powerful and interesting. And then for the two-dimensional system, of course, we should specify the thickness. Here I specify 1.0 angstrom, which means all the generated phases, their thickness will be equal or lower than 1.3. And in the meanwhile, one thing should be noted. All the relaxed phases, if their thickness is greater than the thickness S plus 3. So here in our case will be 1 plus 3. If their thickness is greater than 4, they will be discarded. I mean, they will be abandoned. It makes sense. And besides the thickness, another one is the vacuum. Always for the two-dimensional, we need a large enough vacuum to avoid the interaction between the neighboring layers. Generally, the 12 angstrom is enough, but I prefer to use the 15. Some people may notice that I specify number 15 for 5 times, which is according to the 5 VASP optimization needed later. So that's the reason why we have the 5 times.
Okay, Busheng, people are asking in the chat where can they find the examples?
Okay,
I uploaded the PDF file on the site, on the repository on our site, but probably.
Okay, I paste again. There's a Google Drive link. You may download the example file and maybe as well the hands-on document through the Google Drive link. But for the example file, don't worry, we may build it based on the examples of the use specs. Okay, I think we may continue, right? Okay, so I think the zip. Yeah, there's a zip file. There's a zip file. Maybe you are using. Well, maybe forgot about that. I think we may build it based on the example of the use specs. Don't worry about that. So first, let's continue. So I think that that's all important parameters which is related to the 2D materials in the input file. Then I think we should move to the submission folder. According to Zari already explained detailedly about the submission folder or check state script. To be honestly, as a user, I'm strongly suggest that every user who is planning on the local machine, we should be very, very careful about these scripts, because to make sure they are already adopted to our local cluster, the job managed system, PBS or Slim. Beside that, as well as the queue, the queue partition and the number of codes, we should be very careful about this. And for the lucky one who are planning on the OLIC, yeah, everything is prepared perfectly in the example. But for the others, I mean, the one on planning on the local machine, we should be very, very careful to make sure all the calculations will be running well in the later. And about the execution, I think, yeah, after so many tutorials, I think you're already very similar about how to execute them. But yeah, how to execute it, or through the script to submit it. And in the final, when we submit it and waiting for a long time, we always expected what kind of a result will be provided by the USpecs. So I would suggest we may have the processing of the USpecs, I mean, generation by generations information in the output file, and the best phases in each generation in the best individuals, and the good structures ranked according to the ranking order, and their structure information based on the VASP postcard format. And in the final, yeah, it's about the visualization. So generally, we may consider two ways. Me personally, I would suggest two ways. The first one would be the VESTA way. Would be, I mean, the visualization is beautiful and powerful. But besides that, I also suggest you may consider using the GDIS, actually, which is developed by the Dr. Hubert. You already saw him. Yeah, it's very convenient, which is already interfered with the USpecs. But unfortunately, as far as I know, the GDIS is not supported for the newest version 10.4 right now, but will be updated in the following days. So you may consider. So I think for the first part, yeah, I think the tutorial, the hands-on part. Now I'm going to shift to the terminal on the machine. Wait a moment. Can you sharing? Okay. Is it clear? My terminal, I mean the color, is it clear for you? Okay. So I'm going to make a new one, maybe with my name, go inside it. For the lucky guys who are on the OLIC, you may get the examples from the temporary file, I think, yeah. And it's a package named day3 tutorial 6 two-dimensional materials and the service, and copy them on the local. I will begin with the one I prepared well on the cluster. If you got them, and package, and go inside. We may notice that we have two examples here. So now we are firstly dealing with the first one. So and here, yeah, let's begin with the, okay, yeah, I think we should follow the tutorials firstly. Let's have a look how to module all the necessary codes on the OLIC. And you may notice that the VASP 10.4 and the Python 6. So I'm going to use module load Python 3 and 6 and USPEC 10. And in the meanwhile, consider we needed the VASP. So I'm going to modular this. Yeah, now we have Uzbek. Yes, we got them. Okay, so the first part, we already make sure all the necessary code is available for us, I mean, for the count I'm using. Then let's have a look about the parameter. Yeah, considering so many times about the explanation about the parameters, I think no, we don't need too many times on each of them. So about the calculation type, we're going to use -2 for the isolated two-dimensional material. So -2, 0, no molecule, and non-variable composition. And the thickness, I specify here 1.0 axon because this is what I expected. Of course, you may specify 1.5 or 2 or even 3, just to make sure you are totally clear what you are looking for. If you are expected the think system, you may increase the thickness. And the vacuum, yeah, 15, 5 times. Consider we are going to run the VASP optimization 5 times. And I may take a little bit more time on the number of the 15. As we all know, you know, the vacuum size may be reduced after the optimization. And if we would like to make sure always the vacuum is large enough to avoid the interactions, so every time we set a 15 to refresh the vacuum size. Yes. Yeah, the command is correct. Could you please copy the path to the example file? Yeah, I think, yeah, thank you, Jen. Yeah, and that's the reason we refresh the vacuum size just in case to avoid the interaction between each layers. And the opti type will be the energy, and atom type, yeah, because we're dealing with the silicon, so Si, and number of species. Actually, this one I set it for the unit cell, but we may ignore it because considering in the meanwhile, I also set the minimum atom and the maximum atom. So in fact, all the structure generated by the USpecs will be ranged from 2 to 8 in each cell. And the populations, considering we are dealing with the practice example, so a relative small number is setting here 20, but I would suggest to increase it if you are dealing with a serious topic. I mean, it's not practice anymore. So here we're going to use the 20, considering the time consuming, we may get the result as fast as we can. And the 40 number generations and the stop criterion 8. And you may keep using the operators from the example 5, each of them actually. We may leave it. And the initial code 1 refer to the VASP, and 5 times 1, which means we're going to do the 5 times VASP calculation for the optimization. And about the K-RAS solution, yeah, when we keep to actually all the examples provided by the Uzbek code, by the Uzbek group is already well examined. Generally, we may keep the vote parameters from the examples. And here is kind of important. It's quite related on the job management system. I mean, in different cluster, you may, sometimes the comment may be a little bit different. So on the OLIC, we're going to use the comment like npram and the VASP std and the comment that will be used in the summation script. But you may also consider, leave it empty here maybe, and specify the comment in the script. I think it is also works. And the number of parallel, I set it here is 10, which means after the USPEX is running, it will be allowed 10 structures optimization in the meanwhile. If you increase it, of course, you will be accelerate the speed of the USPEX searching. But considering we're on the OLIC, the number of participants, seems like we're going to have 50. So I guess let's just keep the 10 for this practice. And another thing I would like to remind you is in the specific folder, the potential for the VASP calculation. Don't forget about, when you change the system, don't forget about replace the protocol. Okay. And about the submission, I think Zaid is already explained very well, detailedly about the information inside it. If you are planning on your local machine, you just follow Zaid's suggestion to modify it. Make sure the submission script and the check status script are working well for you. It actually is very, very important. Remember to do this. And yeah, I think it's already, we may submit it. And let's have a look about the script for submission, the USPEC. So the partition, we're going to submit it to the debug partition. And yeah, modify something here. About the time, I think 1 hour is not enough because based on my testing, totally 40 generations needed for this examples, and it takes me around 14 hours totally. So at least I will suggest you use 20. I don't know if there's a maximum limitation about the time of OLIC, but let's first try about the 20. And note one, yeah, consider it's not parallel calculation, so 1 core is enough. And about the job's name, I would suggest you modify it by your, to make a difference about your jobs and from the others. So maybe I will name it and here, yeah, make sure you already loaded the job, the USPEC code, and the similar loop command to make sure the USPECs will be running in a loop, make sure will be finished. Okay, so to submit it, I'm prefer to use through the script. So I'm going to submit it by batch. Consider it a slim system, batch example to the, yeah. Okay, so we got the batch job. I may check, actually, we may check the job status according to the job ID or with the user's name. So quickly. Lock. Oh, sorry, I missed something. Yeah, as you. Okay, I think connection is unstable. Yeah, we may see from the log file, we may notice that. So for the first generation, there are 20 structures, phases generated by the USPEC. And the Z will be ranged from 1 to 7. And with this different symmetries. And then will be submitted to the queue for the VASP calculations. Yes, I think it's mainly the way how to prepare the two-dimensional specs jobs and how to submit it. About this part, if you have questions or some issues, please don't be hesitant to present them in the chat panel. So it's 24. Okay. 24, maybe if we may still have five minutes to see how to analyze the result. So in the reference, there's one I already tested. Here's one result. Yeah. So mainly in the output file, we will have brief information about the parameters, which is for this job, about the and the initial code, which is used for this key resolutions. And most importantly, we may notice here the structure ID, how it's generated from the random. Of course, for this one, it's generated randomly, and the compositions, their energies, and thickness. Be careful about this. Try to remember there's a rules about how to select it after the relaxation. If a structure his thickness is larger than the default one plus 3, it will be abandoned. I guess we may found someone who is abandoned here. As I remember, for the one abandoned, their enthalpy will be recorded at the very huge ridiculous number. So it seems like in the first generation, yeah, considering the thickness is quite small, yeah, they are normal, they are well finished and rated by the USPEC. Let's go from to the second one. Yeah. In the third generation, there's one phase, the composition is 8, and let's have a look about the thickness. Its thickness 4.75, which is actually larger than the 4. So obviously it's abandoned because you may notice that his enthalpy is recorded at the very huge number. It will be never selected as the good structure as the parent for the next generation, because we may understand that for the two-dimensional system, the thinker you are, the lower energy you may get it. So it's a very clever way, I mean, designed in the USPEC to avoid such structure that we are not expected. So this is one of the things I would like to share with you. Be careful about the thickness and note that there's such information, related to the best structures. Okay. And in the best individual, oh shit, it's not so clear. Okay, how about now? Here we may note it here recorded the best structure in each generation, considering it takes totally 14 generations. It recorded here the 14 good structure. I mean, the best structure of each generation. You may have the enthalpy here, the thickness, the surface area, and all the information. And also in the good structure, I mean, in this file, all the phases are ranked according to the order from the lowest to, I mean, the lowest two phases and the second, the third one. Based on my experience, I generally would like to get the final result of the two-dimensional system from the structure information, I mean the postcard in the VASP postcard format. They are recorded in the good structure postcards in this file. I didn't understand your message before. Okay, it's not for me. So we may got their postcard structures from this file. Now you may download, you may download it, the reference, the reference for the silicon VASP based on the hands-on tutorial that I prepared, use scp command, download it to your local, to the Vesta. We may have a look how they look like. Now I will going to shift it from the terminal one to the VASP code. Yeah, by the way, unfortunately, this is not available for this moment. So we're going to use Vesta to have a look how they look like. So new sharing. Okay, so I open my Vesta code and I already downloaded my reference, I mean the result. So if you already follow me, please, you may open the good structure postcards, this file with the Vesta. So I drag it into the Vesta software, and we may notice, so here it seems like we are going to have 20 totally different files according to the good structure ranking order. So this one will be the first one, which is, and if we like,
బట్ ఏంది అంటే రేపొద్దున నా పిల్లలు అది చదివి తప్పు నేర్చుకోవద్దు కదా.
Hello.
సో అట్లా నా పిల్లలు తప్పు రాంగ్ నేర్చుకోవాలని నేను అనుకోను. సో ఆ ఉద్దేశంతో రాశాను.
Okay, let's continue. So we may increase the boundary. We may have a look from the top side. Obviously, it's a kind of bilayer. Anyone? I think that is not the question for me, right? Okay,
No, I think it's not.
Okay, I know that there's a question in the chat panel, but seems like he's sending it from privately to me, so I will read it. I got an error message. Do you know what to do? Use Uzbek version 10.4, version 90, version not found it, required by VASP. So I assume that you are running the calculation on your local machine, obviously, and required by. So my first question will be, did your VASP is available? I mean, for the normal examples, or it's related to the Uzbek? Anyone could help me about this question, because I'm not sure it's related to the VASP code or Uzbek. Okay, Ubek, do me a favor. If you know about this, please, could you answer it? Yeah, thank you. So let's continue. So this is the first phase from the good structure postcard. we may go to see the second one. This one looks beautiful. The third one, you know, all these structures are recorded in this file, and you may have visualize it. You know, it's a very convenient. And I think that's all for the first part. And yeah, do not be hasty to present your question or something else. But about the code, I mean the error code, I'm afraid I cannot do help a lot about the code. Okay, so I decide to shift it to the second part. So I'm going to share the screen. Second one. Okay. Second one, yeah, I guess we're already shifted back from the hands-on tutorial. So the second part is about the surface system mechanism oxide using the GOP combined with the Uzbek code. And to be honestly, I'm not an elite user in the surface system. So any one of you, please feel free to give your comments or corrections or supplements. Yeah. So let's begin. So the step one will be quite similar. Make sure the Uzbek and the GOP is available for us or for you to make sure the calculation will be run well. And the second one, create the specific folder, get the prepared example to inside. And for the surface system, I would like to take more time on the parameter on the parameter settings. So in the input files about the calculation type as we or as you expected. Yeah, here we are going to use 2 for the dimensional for the surface system and non-molecule again and non-variable composition. For the thickness S, here the big capital S refers to the surface region. So the 5 is designed for the thickness of the surface region, and the thickness B refers to the buffer region of the substrate. So we specify the three angstrom here, and for the reconstruct, we are using 4. Actually, here is referred to like maximum multiplications of the cell. I guess it's a kind of similar with the minimum or maximum, you know, with more multiplications, it could provide it more possibility to reconstruct the surface. And about this symmetry, the plane symmetry group is used from 2 to 17. And here again, for the 2-dimensional system, the vacuum is always important to avoid the interaction between the neighboring layers. So consume the calculation 4 times. So we specify 4 numbers here from lower to up. So 10 for the first step and 15. Then in the final step is 20 angstrom is used. And beside the parameters in the input file, there's another thing is we should be careful with is, you know, for the surface, considering the surface and on the substrate. So we need to prepare a postcard substrate in the calculation folder, which is in the postcard format. inside we should prepare it as the geometry information about the substrate region. No need with the vacuum, only the bulk crystal, it's enough. Then another different thing is, for this case, considering the number of atoms inside the system, we are going to use scope. And without the submission, we're going to run it without the job script. Only use one course for one scope calculation. In fact, the speed of calculation is quite quickly. It takes me only one course for this job. It takes me 3 hours to finish the first generation, which contain 40 structures totally. So to be fair, I feel it's kind of quickly. And about execution, the same using the VASP R refers. Yeah, finally will be the analysis the result, kind of similar with the two-dimensional, 2D silicon, the same process information in the output, and the best individuals in the best individual files, and the good structures and their postcards. And again, about the visualization, we're mainly going to use the Vesta. Okay, now let's move back to the machine on the terminal. Okay. Sharing. Okay, so we're back to the terminal. So let's go inside the service example, and here, yeah, I think we may accelerate the speed, considering we already explained the parameters in the hands-on tutorial. So 200 here refers to surface system, and the thickness for the surface region, and the 3 extron refer to the buffer region, and the maximum multiplication of the cell, and number species is referred to the 4 magnesium and 4 oxide, and the plane symmetry, and the pop size. Yeah, let's just keep it as provided by the USPEC example. And the operators, the same from my point and experience, the operators provide based on the examples always works well for different kind of systems. So for me personally, I would prefer to keep them. And here, considering we are going to use not submitted to the queue, which means we're just running, we're not going to submit it by the separate jobs. So here we're going to use the num job script 0, and number of parallel will be 1, of course. And the ab initial code, we're going to use the gulp. So 3 here refers to the gulp, 4 times refers to the number of the times of the optimization. And the comment of the executable. Yeah, I think if you already finished the tutorial of the and the vacuum 4 times for the 4 times optimization. Okay, when the input file is prepared well. And also here in the postcard substrate. So in this file, we should prepare the substrate in the postcard format, but without the vacuum. We should be noted that no need to set the vacuum, only the bulk phase, yes. And go inside to the specific, check again. Okay. For the gulp, seems like no need for the postcard version of the potential file. So I think yes, and in the final one, let's check about the partition function. Yeah, we're suggested to submit it to the debug partition. And about the time, I think we need to increase it. Based on my experience, it takes me totally 18 hours. So I will also suggest let's use 20 and one node, one course, and the name to just in order to make difference with all the jobs, use something you may note easy to recognize it's your job. Yeah, and don't forget about to module the necessary code inside the script. And the final, the command to execute it, to run the USPEC. So I think everything is prepared pretty well. So let's have a we're going to use batch service. Okay, so I prefer to let's have a check the job status user 15. So this one is mine. Yeah, the others is about the 2D silicon jobs. Okay, let's see this running well or not. Yeah, okay, yes. Specified by user. Okay, seems like the optimization type is forgot it, but seems like the default one is as well as. And the structure is again generated by the user. And we may just wait. Yeah, let me just wait. If you have question, you may post it on the chatting panel. Okay, and we have 40 minutes left. So we may keep let the jobs running on the queue. And let me have check all this. No. I forgot about that. So I prefer to shift it how to visualize the result. Yeah, and the same using the SCP comment to download the result and using the Vasta to visualize it. If you already got the examples, you may have a look from the result in the reference inside. Okay, I'm going to shift from my terminal. Okay, so I'm going to import it, the result from the service. So it should be, yeah, we may begin from the unrelaxed. Yeah, we may begin from the gather post call unrelaxed. Okay. For this one, yeah, just to be noted, this one is unrelaxed, which means initial one generated by the USPEC. And totally, seems like we have candidate 526. It looks different. The service region on this, and we may notice. Yeah, this one looks good. Different kinds. The USPECs based on the symmetry operators, different kind of operators algorithm. They presented different of the service mode. Okay, now I think we may shift to the good one. The good. So seems like this is the final result. We got it, and it looks pretty well because I'm pretty sure the symmetry is very high because the surface region is totally, I mean, I may not say totally, but quite close to the substrate. And seems like this is the only one we got it. Yeah, seems like even in the good structure, it's only one structure recorded in site. I think that's why we got one postcard in the good structure. If anybody from the Uzbeks group who developing the service, service system, if you have more detailed information about why we only have one good structure from the results, you may share with us. Okay. And let me check the calculation. Yeah, in my case, the service example is still running well in the OLIC cluster. If your calculation have some error or something else, please feel free to share with us, or any comments. You know, as I told you, I'm not elite user on the surface system. So if I did something wrong or something else, please feel free to comment or correction. And I think I already finished the two part of this tutorial. If you have question, yeah, you may ask. Okay, there's a new one. How the thickness varies after relaxation? The thickness of substrate is fixed. It's a good question about the thickness, surface, and the buffer region, how they relies after relaxation. I think from some point, both of them are changed from some point, but maybe not too much. And to the second question, the thickness of the substrate. Actually, if I understood correctly, in the substrate part, the buffer one could be relaxed, but the rest, they are fixed. I think this is my answer to your question.
May I add some remark?
Yeah, of course.
Because actually it was me who implemented this code long time ago. So the way we deal with this is the following. So we have a substrate. We also have a buffer region, and we have substrate. So the substrate will contain a few buffer region items, and then we have a surface region. So in the buffer region, we allow the atoms to relax. So the atoms has the freedom to move anywhere. And then on the surface items, of course, we also allow them to move. Yeah, so if you consider your surface model, so the entire the length in C direction, the thickness does not change because we don't optimize the lattice, but the height of the atoms can change. So sometimes, so for instance, you have your initial surface atoms in the surface region, but after optimization, probably there is a chance that the atoms can go to the vacuum region as well. So in this case, we consider this a possibility. But so what will happen, like if the atoms is flying to the flies to the middle of the vacuum, so usually we will just delete these atoms because we know this is not a good structure.
Thanks, John, for your answering, and I hope it's clear for you, Nilim.
Thank you very much for your answer. Thank you very much.
So, any questions? Yeah, the final 5 minutes. Okay, I think there's no more question. Vladimir or Alice, I think, yeah, the tutorial is close to the finish.
Yeah, okay. Sorry.
So I'm going to
Yeah, that was the positive feedback example. Okay, so thank you very much, Bushen.
Okay.
And at that point, Artyom should have started his final remarks, but unfortunately, he's, as it happens very often, he's super busy. So he asked me to make some conclusion remark. And first of all, I would like to thank all of the participants and all of the lecturers, tutors, because it was really, well, we were surprised by so many people of very high academic level joining our conference. And special thanks to Alisa, who was really a superhero with superpowers, as we noted before, because she took a very huge burden of organizing this technical part, and also had this correspondence with participants and lecturers. And now we don't have Artyom here, but we have all of the key developers of our code. So you are free to ask any questions that you are interested in. We have here Zahed, we have here Pavel Bushlanov, we have Artyom Samsevich, who is responsible for, yeah, thank you, Alice. We have Artyom Samsevich, who is responsible for the transition path prediction, and actually almost all of our team. So you are free to ask any questions that you have about USPEX code. And by the way, I didn't guess that I will say this anytime, but as a real YouTube blogger, I can say that please write in the comments whether you like this format, because actually we think that in the future we will probably keep the tutorial part mostly online, because I think this is more efficient, more effective than offline format. But the conferences will be offline, of course, because it is important to meet face to face. Okay, thank you, and we're open for your questions.
talk queue times. Yeah, it's an issue, for such an international conference. It's really not easy to match the time, to make sure everyone are staying the
Yeah, but this is still a very good opportunity to have
For sure.
very busy people from all around the world here. Yes, it is quite an issue to, for example, for Changju to stay up at 5 a.m. So yeah, but it is, I think it is easier to get up at 5 a.m. than to go all the way from Las Vegas to Russia and then back. Yes,
Yeah.
yes, and
Yeah,
Uber
the advantage of attending the conference, a virtual conference, is that you can actually, for instance, I don't have to. I just need to wake up. I don't have to get up.
Yeah.
I can just lie in the bed and then watching the videos.
Okay, guys, I think for the questions you can ask them directly, not in the chat.
There's a question related to how long they may keep using the count on the OLE cluster.
I already answered this. We will keep this. Sorry, I will let Zahid in. We are going to keep the accounts until Monday. So you have 2 more days to
enjoy the VASP.
A question about, sorry, open the chat. Oh, I see a lot of questions. Question about transition path sampling. So I think we should address this question to Artyom Samtsevich. Artyom, are you here?
Yes, I am. Let me check. What was the question?
A question from, I think, where you can ask directly again, because now we are in the, like the
I see it in the chat. Yeah, okay. 1 minute. Sorry, I closed it. Apparently. How to visualize TPS results? Let me think. Actually, because I didn't touch this kind of calculations for a long time, so I have to refresh it in my mind and check what kind of results folder look like. And I guess that just write me an email, and I guess like in several days I will give you a proper answer how to visualize it and how to interpret that data and that kind of files that is in results folder, because I really didn't touch it for a long time, so unfortunately I cannot answer it right now.
Anytime, okay. Thank you very much.
Yeah. Send me an email and I will reply.
You can ask Vladimir my email.
What?
You can ask Vladimir. He's gonna give you my email.
All right.
Okay, I will. Yes.
Thank you.
So guys, any more questions?
I have a question. Can you hear me?
Yes.
Perfect. I have a question regarding the bank gap. I already wrote it down a few times. I was trying to run the example 1 in the previous version, and apparently I miswrote the bank gap requirement. Can you please specify what was wrong and write down the correct version?
Excuse me, I don't understand.
Zahid, we barely hear you.
Sorry, again, tell me.
Habib, can you repeat the question?
Yeah,
No,
sure.
no. You told me, you asked what is the problem, but I don't see any error message or whatever to tell you what is the problem.
Yeah, I can resend the error message. It is to the chat.
I was away a little bit, so I don't have the chat on my phone.
So I can read the error out loud. The error using eval, undefined function or variable band gap. Error in calc fitness 300. So undefined function or variable band gap. I guess it means that I wrote it incorrectly.
Yeah, yes, we both resent the question in the chat.
Okay.
Perfect.
Okay, I suggest the next question. The next person asks his question. I'm checking if there is something wrong with what you wrote here or not. First, okay.
Basically, until the point when the band gap calculation is required from the input, all calculation goes correctly. So in the end, I received the file with enthalpy, with the relaxed structures, but this part, the band gap is missing. Thus, the overall calculation stops. Are you there?
Yes, I told please let other people ask question. I'm checking in the code to
sorry.
understand if there is any problem with what you wrote or not.
Sorry.
So Vova, please see if any other people have a question.
Yes, I'm looking into chat right now. Thank you all. Thank you guys. A question from Carla Nervi to me directly. We're very much interested in molecular crystals, so we will be happy to help in debug. I did conversion in helping in development. Oh, you're very welcome, Carla. So I think.
Thank you, Vladimir. Nice to listen to you.
Yes, nice to have you too.
Yes, I think very general question. So it's because we are really trying to use USPEC for molecular crystals, and sometimes we get a little problem or incompatibly. So we always slow down in this process because we do not exactly catch the point where it's necessary to solve the bug. And so since we are moving in this direction with a PhD student that is working in this field, and she's I think she is connected also. We are happy to help in any way is possible for debugging and advancing the code. So of course, you can take your consideration with Artyom and other members of the group. Thank you.
Yeah, thank you. I know that these molecular crystal calculations, they are usually require some time and effort to be run smoothly, because I also have colleagues who do this. But me personally, I'm more focused on nano clusters. So I think that this message is more to the developers, the major developers of our code. So now we're translating the code from MATLAB to Python. So I think we will probably like consult you when we were implementing the molecular crystals in the Python.
Great, thank you.
Thank you. Okay. Please put all the tutorial materials in one place. I didn't have access to any machine. Okay. They are actually already put in one place, except 2 tutorials led by non-USPEX developers. So now I will put the tutorial by Uber about GDs to our site. And as for the tutorial about machine learning interatomic potentials, I think I will put there the link to their site. Thanks so much. Some technical issue from Lucas Francisco. I think I pronounced it correctly. Structural segmentation fault. Don't think I can help with this.
I guess that I can comment that last question regards quantum espresso. So I guess it's better actually to run that kind of calculation not via which cluster is 0. That means that if you are doing so, you are running it on a head node of your machine. If it is fine, if it's your PC or your laptop, but it's better actually to run it on a high performance computer. And if you do so, it's better to write which cluster 1 and then specify submission scripts. So which way you are using actually to run that calculation? Yeah, that was the question.
May I ask Habib? Habib, are you here?
Yeah, I'm here.
Did you see what I wrote you in the chat? Did you specify it like what I wrote, or you forgot the last part of the op type like in your input?
Yeah, sorry. So I wrote 1, then the space and the mean, band gap, etc. No, I didn't copy this last part. It's there in the input file, so I just didn't copy it.
No. I mean the last line. Do you have the last line and op type?
Yes.
And they should be in 3 lines, of course. I'm just asking to understand. If you, in your input file, you have such things as I wrote, plus enthalpy, of course. I forgot to add enthalpy or 1. It should work. If it does not work, please tell me. I need to check it. And if there is a bug, I need to fix it.
I just posted there. So this is how it looks. The full one, it's op type 1, then the band gap, and then yeah.
No. Not like this. It should be in 3 lines. It's generally, I mean, should not matter, I think, but something like this.
Yeah, it's exactly the same. Yes.
Okay, so let's keep in touch, and I will check this if there is a bug or not. By the way, I will send my email here, so everybody who has a bug or report a bug, to send me an email separately with that bug so I can check it. If I asked you to do it, because sometimes it's not a bug.
So the question, should I send it? Is it a bug or you still need to check
No,
it?
no. Please send me an email so I can inform you at least. Right now, I know what is your problem, but at least I can inform you if it's a bug or how it can be fixed. Or if it's a bug, I will tell you, for example, we fixed it, so you can release and update your version.
All right, thank you.
Yes, I just wrote my email.
Thank you very much.
Yes, thank you. By the way, Lucas asked me how to turn off the random generator. I already told it in the chat, but I will write it once more. You just need to add one line to just give 0 fraction to random topology. I will write it again.
Ladies and gentlemen, I think we can officially close our conference right now, and those who want to continue the discussion may stay. And now I think it's time to stop the recording and live translation. So thank you very much.